Beyond our familiar blue sky lies a universe brimming with enigmas. From the violent hearts of stars to the silent voids between galaxies, space challenges our understanding of reality. Join us as we embark on a cosmic journey exploring phenomena that defy explanation. We'll explore the secrets of black holes, the hunt for alien worlds, and probe the nature of time and space itself. Beneath the dense, toxic clouds of Venus lies a highly fascinating yet hostile environment. The atmosphere is primarily composed of carbon dioxide, with clouds of sulfuric acid, creating a pressure about 90 times greater than that of Earth at sea level. This immense pressure, combined with scorching surface temperatures reaching around 450 degrees Celsius, makes Venus the hottest planet in our solar system. The surface itself is a rocky landscape dotted with volcanoes, valleys, and vast plains. Geological features suggest that Venus is geologically active, and there are signs of ancient lava flows that likely reshaped the terrain. Interestingly, there are over 1,000 major volcanoes on the planet, some possibly still erupting, which raises intriguing questions about volcanic activity and planetary evolution. One of the most surprising revelations from missions exploring Venus, such as the Soviet Venera probes and more recently the European Space Agency's Venus Express, is the existence of mountainous regions like Ishtar Terra and Aphrodite Terra. These areas host highland terrains, suggesting that geological processes have led to significant changes in the planet's surface over time. Exploring the secrets that lie beneath these thick clouds can offer insights into not just the history of Venus, but also the processes that shape rocky planets in general. Understanding the atmosphere and surface interactions, as well as any potential signs of past water, transforms our perspective on this enigmatic neighbor. The quest to learn more about what lies beneath continues, capturing the interest of scientists and space enthusiasts alike. The possibility of life existing in the subsurface oceans of Europa and Enceladus tantalizes scientists and stirs the imagination of many. Both of these icy moons in our solar system harbor hidden oceans that lie beneath thick layers of ice. Europa, one of Jupiter's moons, is believed to have a vast ocean, potentially supporting conditions that could be favorable for life. Enceladus, an icy moon of Saturn, has also revealed exciting evidence of a salty ocean beneath its surface, especially through geysers that eject water vapor and organic molecules into space. The environments of these subsurface oceans share intriguing similarities with some of Earth's own extreme habitats, such as hydrothermal vents. These vents provide a source of heat and nutrients in the dark depths of the ocean, creating ecosystems that thrive without sunlight. Similarly, if there are hydrothermal activity and chemical reactions occurring on the ocean floor of Europa or Enceladus, they could create suitable conditions for life to flourish, even in complete darkness. In addition to the potential for liquid water, scientists have detected organic compounds in the plumes of Enceladus and believe that Europa's surface is enriched with various materials that could provide the necessary chemical components for life. The search for biosignatures, indicators of past or present life, is a driving force behind missions targeting these moons. Future missions, like NASA's Europa Clipper, are designed to scrutinize Europa's surface and subsurface components more closely. While we have yet to find direct evidence of life beyond Earth, the intriguing conditions present in these subsurface oceans suggest that they could potentially harbor some form of life, no matter how simple. As exploration continues, the answers to these questions may dramatically shift our understanding of life's existence beyond our home planet. Uranus is a remarkable planet in our solar system, not just for its vivid blue color, but also for its unique rotational tilt. This ice giant rotates on its side with an axial tilt of approximately 98 degrees, which means it essentially rolls along its orbit. This unusual orientation is likely a result of a tumultuous history involving collisions and gravitational interactions with other celestial bodies. One prevailing theory suggests that Uranus may have experienced a catastrophic impact with a massive object during its formation. Such an event could have knocked the planet into its current tilted orientation. This collision could have been powerful enough to alter the planet's spin dramatically, resulting in its sideways rotation. It is further believed that this kind of violent history is not entirely uncommon among the gas giants in the outer solar system. The secondary effects of this tilt are intriguing as well. Uranus experiences extreme seasonal variations due to its unique orientation. A single day on Uranus lasts about 17 hours, but its seasons can last for over 20 years given its long orbital period around the Sun, which takes about 84 Earth years. This means that one hemisphere of the planet can experience years of continuous sunlight or darkness as it orbits. Understanding why Uranus rotates on its side sheds light not only on the planet itself, but also on the dynamics of planetary formation and evolution. As we continue to study Uranus and the other gas giants, we gain deeper insights into the processes that shape our solar system and the complexities that arise from its diverse array of planetary systems. Saturn's hexagonal storm at its north pole is one of the most intriguing phenomena in our solar system. This striking six-sided jet stream stretches over 20,000 kilometers across and exhibits remarkably stable structural characteristics. The formation of this unusual shape is believed to be caused by a combination of atmospheric dynamics and fluid mechanics, drawing comparisons to other natural phenomena on Earth. The hexagon is created by a stream of fast-moving air that flows in a jet at high altitudes, where the colder atmosphere interacts with warmer air below. This interaction creates a wave pattern in the atmosphere. The six-sided shape arises from the balance between the speed of the flow and the rotation of Saturn. It is similar to the way a rotating fluid can develop polygonal shapes when subjected to certain velocities and temperatures. The stability of the hexagonal formation is quite remarkable, persisting for decades or even longer, as evidenced by images taken by the Voyager spacecraft and later the Cassini mission. The dynamics of the hexagonal storm are not fully understood, but scientists are actively studying how such structures might form and persist in large planetary atmospheres. The conditions on Saturn, including its rapid rotation and extreme atmospheric temperatures, create an environment ripe for such unique weather patterns. The interactions between different layers of its atmosphere contribute to the continuous activity and evolution of this striking feature. What makes this hexagonal storm even more compelling is that it has been observed on other planets and moons, leading researchers to ask whether similar dynamics are at play across various planetary atmospheres. The ongoing fascination with this storm illustrates Saturn's complexity and the broader principles of meteorology, shedding light on atmospheric physics beyond our own planet. The bright spots on the dwarf planet Ceres have captivated scientists and space enthusiasts alike since they were first observed by the Dawn spacecraft in 2014. These bright areas, primarily found in a large crater called Okator, are believed to be composed of sodium carbonate, a type of salt that reflects sunlight more effectively than the surrounding darker material. The presence of these bright spots suggests that Ceres has a history of geological activity, particularly involving briny water. One theory posits that the bright spots are formed by salt deposits left behind after briny water has traveled to the surface and evaporated. Ceres hosts a subsurface reservoir of water ice, and this created the conditions for brines to seep upward through fractures in the crust. When the water reaches the surface, it may freeze or evaporate, leaving behind the bright salt residues. This process indicates that Ceres is not a completely inactive body, but has ongoing geological processes that shape its surface. The continued study of these bright spots has revealed a complex interplay of factors. In addition to sodium carbonate, researchers have identified other minerals, such as magnesium sulfate, further indicating the presence of liquid water in Ceres' past. The bright spots serve as a window into the dwarf planet's interior and its thermal history, providing clues about its evolution and the potential for organic chemistry. These findings have broad implications not just for Ceres, but also for our understanding of other celestial bodies in the asteroid belt and beyond. The discovery of bright spots reinforces the idea that even small bodies in the solar system can harbor intriguing mysteries and dynamic features, challenging our perceptions of their geological and chemical processes. Tomball Regio, the heart-shaped region of Pluto, is one of the most captivating features discovered during the New Horizons mission in 2015. Spanning over 1,600 kilometers wide, this vast landscape is primarily made up of a large, smooth expanse of nitrogen ice. The region's shape and characteristics have sparked a wealth of scientific inquiry and curiosity about what lies beneath Pluto's frozen surface. The smoothness of Tomball Regio suggests that it has undergone geologic processes relatively recently in the context of Pluto's history. This indicates that the region is geologically active, challenging the notion that Pluto is merely a static, frozen world. The surface displays various features, such as ridges and possible cryovolcanoes, which hint at a rich history of internal heat and possibly the presence of subsurface oceans or reservoirs of slushy materials. One of the most intriguing aspects of Tomball Regio is the area known as Sputnik Planitia, which forms the left lobe of the heart. This region was identified as a vast plain dominated by large nitrogen ice, where the unique polygonal patterns suggest convection processes at play. This reaffirms that Pluto's surface is not just a frozen shell, but is influenced by complex interactions involving heat, pressure, and volatile substances. The exploration of Tomball Regio and its features not only provides insight into Pluto's geology, but also contextualizes our understanding of other icy bodies in the Kuiper Belt and beyond. The investigations continue to surprise scientists, offering a remarkable glimpse into the dynamics and evolution of this distant world, which continues to captivate our imaginations and urges further exploration of the outer solar system. Mercury's core is remarkably large, making up a significant proportion of the planet's total volume, and this unusual characteristic has intrigued scientists for years. About 70% of Mercury's radius is composed of its metallic core, while the outer silicate mantle and crust are relatively thin in comparison. This raises a fascinating question about the processes that shaped Mercury during its early formation. One prevailing theory suggests that Mercury's significant core size is a result of a series of massive collisions early in the planet's life. During the formation of the solar system, planetary bodies experienced frequent impacts as they accumulated material. Mercury, being closer to the Sun, may have endured more intense and energetic collisions, which could have stripped away much of its mantle, leaving behind a larger metallic core relative to its overall size. Another factor to consider is the planet's proximity to the Sun. The intense heat from the Sun may have affected the materials that formed Mercury, leading to a composition that favored the retention of heavier elements, such as iron. This could have contributed to a denser core, thus amplifying its relative size compared to the outer layers. Mercury may have accreted from a mixture of materials that had a significant metallic content, leading to its current structure. Recent studies and data from the Messenger spacecraft also support the idea that Mercury's large core plays a role in its magnetic field. Though weak, this magnetic field suggests a partially liquid outer core that could generate a dynamo effect, further emphasizing the importance of its surprising internal structure. Understanding the reasons behind Mercury's unique core allows astronomers to piece together the complex history of planet formation in our solar system, providing insights not just into Mercury, but into the nature of terrestrial planets as a whole. Mercury experiences some of the most extreme temperature variations in the solar system, with surface temperatures ranging from sweltering heat during the day to freezing cold at night. This dramatic fluctuation is primarily due to Mercury's lack of a substantial atmosphere and its slow rotation on its axis. While the planet orbits the Sun at an average distance of about 58 million kilometers, it has a very thin atmosphere composed mostly of oxygen, sodium, hydrogen, helium, and potassium. This thin atmosphere is insufficient to trap heat, resulting in rapid temperature loss during the night. The planet has an axial rotation period of approximately 58 Earth days, meaning a single day on Mercury lasts longer than its year, which is about 88 Earth days. During the day, temperatures can soar to around 420 degrees Celsius as sunlight bathes the surface. In stark contrast at night, temperatures can plummet to around -170 degrees Celsius. exposing the extreme differences that occur across the planet's surface. Additionally, Mercury's surface composition plays a significant role in its temperature variations. The planet is covered in a rocky, metallic terrain with low heat capacity, allowing it to heat up quickly when exposed to sunlight. However, this same characteristic makes it lose heat just as quickly once the sun sets, leading to colder nighttime conditions. The lack of significant geological features, such as oceans or extensive land masses, which could help moderate temperatures, further exacerbates these fluctuations. These extreme temperature variations present a challenging environment for any potential exploration and highlight Mercury's unique position among the terrestrial planets. Studying these phenomena offers insights into not just Mercury's climate, but also the conditions that can prevail on other rocky bodies in the solar system. Triton, Neptune's largest moon, is fascinating not only for its unique features, but also for its unusual retrograde orbit, meaning it orbits Neptune in the opposite direction of the planet's rotation. This peculiar orbital behavior suggests a violent history that sets Triton apart from its fellow moons in the solar system. The leading explanation for Triton's backwards orbit is that it did not originally form alongside Neptune, but was likely captured by the planet's gravity. During the early days of the solar system, many celestial bodies roamed the outer reaches, and Triton was probably a larger Kuiper Belt object, similar to Pluto. As it ventured close to Neptune, gravitational forces acted upon it, pulling it into orbit around the planet. This capture process typically results in retrograde orbits due to the complex dynamics involved in such interactions. Another supporting piece of this theory involves the energy involved in the capture process. When Triton approached Neptune, it could have experienced significant gravitational interactions with other objects or the planet itself. These interactions can lead to alterations in speed and direction that would further contribute to the Moon's unusual orbit. The net result is that Triton now orbits in a direction opposite to Neptune's rotation, which is rather uncommon for large moons in our solar system. Triton's retrograde orbit has significant implications regarding its geological activity and future. It is believed that the Moon is gradually spiraling inward due to tidal interactions with Neptune. Eventually, this may lead to a catastrophic end for Triton, as it may either crash into Neptune or break apart, creating a ring system around the planet. This intriguing moon continues to be an object of study, providing insights into the dynamics of celestial mechanics and the complex histories of moons in our solar system. Beneath the swirling chaos of Jupiter's Great Red Spot lies a mesmerizing and complex structure. This enormous storm, which has persisted for at least 350 years, is a gigantic cyclonic vortex that stretches an astonishing 16,000 kilometers across. While the storm itself is evident in the upper atmosphere, what happens beneath its turbulent clouds is less visible but equally fascinating. The Great Red Spot exists within Jupiter's atmosphere, primarily composed of hydrogen and helium, but it is also rich in ammonia, methane, and water vapor. Wind speeds at the storm's outer edges can reach impressive gusts of up to 450 kilometers per hour. Below the visible layer of clouds, the dynamics of the storm shift significantly. The atmospheric pressure and temperature increase as one descends, influencing the storm's behavior and structure. Recent research suggests that there is a link between the shallow atmospheric dynamics we see and the deeper layers of Jupiter's atmosphere. The Great Red Spot is thought to extend far below the cloud tops, possibly plunging down to depths where temperatures and pressures become extremely high. This may lead to different forms of energy and fluid dynamics that are less understood but critical to the overall structure of the storm. Furthermore, the potential for deeper systems of circulation beneath the storm might help maintain its longevity. While the outer layer is continuously feeding off the surrounding atmosphere, it draws energy from the underlying fluid motion. This interplay supports the hypothesis that the Great Red Spot is more than just a surface phenomenon, hinting at complex storm systems that reveal much about Jupiter's turbulent atmosphere and the processes driving these massive storms. As we continue to explore and study Jupiter, we may uncover even more mysteries hidden beneath the swirling clouds of its iconic Great Red Spot. life on a tidally locked planet presents a captivating scenario for astrobiologists and scientists, as such a planet has one side perpetually facing its star while the other remains in eternal darkness. This unique orientation creates extreme conditions that could significantly influence the evolution and adaptation of any potential life forms. On the illuminated side, temperatures would likely be extremely high due to constant sunlight, potentially leading to a harsh, desert-like environment. However, the presence of liquid water could be a significant factor. If conditions allow for the existence of oceans, life forms might develop specialized adaptations to withstand intense heat and high radiation levels. These organisms could have reflective surfaces or biochemical mechanisms to cope with excessive sunlight, resembling some extremophiles found on Earth, such as certain desert plants or the resilient organisms in hydrothermal vents. Meanwhile, the dark side of the tidally locked planet would experience frigid temperatures and a lack of sunlight, creating entirely different challenges. Life in this realm could evolve in subterranean environments, utilizing geothermal energy or chemical reactions as energy sources. Here, organisms might develop robust features to survive prolonged darkness, similar to cave-dwelling species on Earth. They might have enhanced sensory perceptions to navigate without light, relying on touch or chemical signals for communication and interaction. The region along the terminator, the boundary between the day and night sides, could represent the most habitable zone on a tidally locked planet, where temperatures are more moderate and conditions might be suitable for life. This area could host a diverse range of ecosystems, allowing for a blending of species from both the sunlit and dark regions. Photosynthetic organisms might thrive here, capitalizing on the transitional lighting conditions, while also evolving mechanisms to survive the unique challenges of their environment. Life on a tidally locked planet would surely be diverse and specialized, reflecting the complexities of its environments and the evolutionary pressures imposed by constant sunlight on one side and eternal darkness on the other. Understanding how life could adapt in these diverse conditions expands our appreciation of the potential for life beyond Earth and may guide future explorations of exoplanets within habitable zones. The search for Earth-like planets in the universe has garnered significant attention, especially with the advent of advanced telescopes and space missions. Current estimates based on data from missions like the Kepler Space Telescope suggest that Earth-sized or potentially habitable planets may be quite common in our galaxy. It is believed that there could be billions of such planets in the Milky Way alone, many of which may orbit stars within the habitable zone where conditions could allow for liquid water to exist. The concept of the habitable zone refers to the region around a star where temperatures allow for water to remain liquid on a planet's surface. This zone can vary based on the star's brightness and size, creating a diverse array of potential Earth-like environments. Studies indicate that around 20 to 40% of Sun-like stars could host Earth-sized planets in their habitable zones, suggesting that our galaxy is teeming with worlds that might share characteristics similar to ours. In addition to the Milky Way, the discovery of exoplanets in other galaxies further supports the idea that Earth-like planets are a common feature of the universe. With thousands of exoplanets catalogued, scientists have identified a variety of planetary systems, showcasing a rich diversity in compositions, sizes, and atmospheres. Some of these exoplanets bear striking similarities to Earth, prompting researchers to explore their potential for habitability. While the presence of Earth-like planets may be common, determining the exact likelihood of life arising on these planets is complex and remains an active area of research. The presence of water, a stable climate, and protective atmospheres are just a few factors that contribute to the potential for life. As technology advances and survey missions continue, our understanding of planetary formation and the prevalence of Earth-like worlds in the universe will deepen, keeping the quest to find extraterrestrial life vivid and compelling. The discovery of exoplanets has revealed a startling diversity of worlds, many of which are extreme in their conditions and characteristics. One particularly fascinating class of exoplanets is known as hot Jupiters, which are gas giants that orbit very close to their parent stars. For example, WASP 121b is a remarkable hot Jupiter with incredibly high surface temperatures exceeding 2,500 degrees Celsius. This heat leads to striking atmospheric phenomena, such as the presence of gases like iron and titanium, which can exist in vapor form. Another extreme exoplanet is HD 189733b, which is also classified as a hot Jupiter. This planet is known for its violent weather, including supersonic winds that can reach speeds of more than 2,000 kilometers per hour. The atmosphere may contain clouds of glass that rain sideways due to the extreme conditions, highlighting the unpredictable and harsh environments that can exist on distant worlds. Exploring the other end of the spectrum, there are planets like GJ 1214b, a sub-Neptune featuring an abundant atmosphere rich in water vapor. This exoplanet orbits a red dwarf star and is especially intriguing because its atmospheric composition hints at the possibility of a water-rich world, potentially leading to conditions that might support life. Then there's the curious case of LHS 3844b, a rocky exoplanet that orbits its star closely. Incredibly, it's hypothesized that this planet may have a molten surface due to extremely high temperatures, leading to a completely uninhabitable environment as it experiences a permanent day side and an equally hostile night side. These extreme exoplanets challenge our understanding of planetary formation and environmental conditions, pushing the boundaries of what we consider habitable. Studying such diverse worlds not only enhances our knowledge of planetary science, but also inspires new questions about the potential for life in the universe, expanding our perspective beyond our own solar system. The existence of diamond planets, composed primarily of carbon, is a captivating concept that has garnered significant interest among astronomers and planetary scientists. These hypothetical worlds could potentially form under extreme conditions, where high pressures and temperatures lead to the crystallization of carbon into diamond structures. Such conditions are thought to arise in planets with compositions rich in carbon, possibly in the form of graphite or other carbon-based minerals. One of the most promising candidates for being a diamond planet is a planet known as 55 Cancri E. This super-Earth, about 40 light-years away, has been proposed to have a carbon-rich composition, which might suggest the presence of diamond in its structure. With a surface temperature exceeding 1,000 degrees Celsius, the extreme conditions on this planet contribute to the possibility of carbon existing in a diamond form, especially considering that its density and other characteristics could align with this hypothesis. The formation of diamond planets is typically associated with planets that have undergone specific evolutionary processes, including significant amounts of carbon-rich materials during their formation and subsequent transformation through geological activity and extreme environmental conditions. These processes could lead to the creation of diamond structures deep within the planet's interior, making such worlds remarkably different from Earth. While the idea of diamond planets is scientifically plausible, direct evidence is currently lacking. Future observations of exoplanets with advanced telescopes like the James Webb Space Telescope could provide crucial insights into their compositions and atmospheric properties, enabling scientists to explore the potential for carbon-rich worlds beyond our solar system. The pursuit of these unusual planets ultimately deepens our understanding of the variety of planetary types that exist in the cosmos and challenges our preconceptions about what such worlds might be like. Living on a super-Earth would be a fascinating experience, as these planets have a mass greater than that of Earth, but significantly less than that of Neptune or Uranus. Typically, super-Earths are rocky, similar to our home planet, and possess greater gravitational pull. This higher gravity would mean that everyday objects, including ourselves, would weigh more. Activities such as walking or running might feel quite different, potentially requiring more strength and endurance. The atmosphere of a super-Earth could vary widely depending on its proximity to its star and its individual characteristics. Some super-Earths may have dense atmospheres rich in gases like carbon dioxide or methane, which could give rise to extreme weather patterns. If it were located in the habitable zone, the conditions might be just right for liquid water to exist. essential for life as we know it. However, the intensity of sunlight and temperature would significantly influence the climate and weather on such a planet. One intriguing aspect of living on a super-Earth is the potential for diverse ecosystems. If conditions allowed, life could evolve in ways that differ vastly from those we are accustomed to. For instance, the stronger gravity may lead to shorter, stockier plants and animals adapted to keep their balance. Additionally, larger land masses could provide expansive areas for ecosystems to thrive, leading to more varied habitats. Exploring the night sky on a super-Earth could be breathtaking. The view of its star, or perhaps multiple stars, would create a stunning celestial backdrop, showcasing unique constellations and colors. With potentially higher atmospheric density, sunsets and sunrises could display more vivid hues. Living on a super-Earth would offer both challenges and wonders, igniting curiosity about life beyond our planet and the extraordinary possibilities of the universe. Hot Jupiters form through a fascinating process that involves a complex interplay of gravitational forces, gas dynamics, and the evolution of protoplanetary disks. These gas giants, significantly larger than Jupiter, orbit very close to their stars, often at a distance much shorter than that of Mercury from the Sun. Initially, these planets likely develop further out in their solar system, where temperatures are cooler and materials are more conducive to building up large masses of gas and ice. As these planets grow, they gravitationally interact with the surrounding material in the protoplanetary disk. During the early phases of planetary formation, potential migrations occur. Various theories suggest that these planets can be nudged inward due to gravitational interactions with other massive bodies in the disk, or through the transfer of angular momentum, which may lead to a spiraling trajectory toward the star. The dynamics are quite similar to a game of cosmic pinball, where the presence of other planets or significant debris influences their paths. Another aspect that contributes to the migration of hot Jupiters is the dissipation of gas in the protoplanetary disk. Over time, this disk can lose its material, which affects the gravitational effects acting on the planet. As the disk's density decreases, the hot Jupiter finds itself pulled inward, moving closer to the star. Sometimes this can be a rapid process, leading to the planet settling into a stable, close orbit around its star. Once a hot Jupiter takes up residence near its star, the intense heat can cause dramatic atmospheric changes. The heat can strip away lighter elements, evoke extreme weather patterns, and even lead to unique phenomena such as atmospheric tides. This close proximity not only raises questions about the conditions for life elsewhere in the universe, but also provides insights into the diverse ways planetary systems can evolve, challenging our traditional models of planet formation and migration. Rogue planets are intriguing celestial bodies that wander through the galaxy without being bound to any star. Unlike traditional planets that orbit stars, these free-floating entities could have formed in a similar manner to their stellar counterparts, but were ejected from their original systems due to gravitational interactions or collisions with other bodies. Estimates suggest there could be billions of these rogue planets roaming the Milky Way, making them a significant part of our cosmic landscape. Surviving without a star presents unique challenges for rogue planets, primarily because they lack the warmth and light found in systems with stars. Many rogue planets are believed to retain some internal heat generated from their formation. This residual heat can create a subsurface layer of warmth that influences the planet's ability to maintain an atmosphere. In some cases, rogue planets may even possess atmospheres rich in hydrogen or other gases, which could stabilize over time despite their isolation. The potential for life on rogue planets remains a subject of intense interest. While the frigid temperatures of deep space pose significant hurdles, researchers speculate that certain rogue planets may harbor subsurface oceans or geothermal activity similar to what is found on some moons within our solar system. If such conditions exist, there is a faint glimmer of hope for microbial life to thrive in these dark, distant environments. Rogue planets also raise questions about our understanding of planetary formation and evolution. Their existence challenges conventional views of how celestial bodies interact, and each discovery broadens our perspective on the diversity of planetary systems. As telescopes and technology improve, our ability to detect and study these enigmatic wanderers continues to enhance, revealing more about the secrets they hold and the processes that govern the universe. The possibility of habitable moons orbiting gas giants in other solar systems is a fascinating topic that has garnered significant interest among scientists and astrobiologists. Gas giants, much like Jupiter in our own solar system, are often located in stable regions of their systems, and their large size can create dynamic environments. These moons, often referred to as exomoons, could potentially host conditions suitable for life, particularly if they are located within the habitable zone of their parent gas giant. For a moon to be considered potentially habitable, it would need a number of essential characteristics. One key factor is the presence of liquid water, which is crucial for the development of life as we know it. Some gas giants could generate enough tidal forces through gravitational interactions with their moons to keep subsurface oceans in a liquid state, even if the surface temperatures are frigid. Moons like Europa and Enceladus in our solar system demonstrate this concept, as they harbor vast oceans beneath their ice-covered surfaces, providing habitats that might support life. Moreover, a moon's atmosphere plays a vital role in its habitability. If a moon can maintain a stable atmosphere, it would be better equipped to regulate temperatures and protect any potential life forms from harmful cosmic radiation. The balance of elements, such as carbon, nitrogen, and hydrogen, would also influence the potential for life. The right conditions might even allow for complex ecosystems to develop within that moon's atmosphere and ocean. However, the search for habitable exomoons brings its own challenges. Detecting these moons around distant gas giants is difficult due to their size and the limitations of current technology. As our observational techniques advance, scientists continue to explore and theorize about the potential for life beyond Earth. The concept of habitable moons expands our understanding of where life could exist in the universe, suggesting that the pathways to life may be more diverse than previously imagined. The sky on a planet orbiting a binary star system would present a breathtaking and constantly changing spectacle. In such systems, two stars orbit a common center of mass, and depending on their relative positions, a planet could experience a wide range of lighting conditions. The most immediate impact would be the varying intensities of light and color, as the two stars could differ significantly in size, brightness, and color spectrum. During the day, a planet may experience a unique illumination when both stars are visible in the sky simultaneously. This scenario could produce striking sunrises and sunsets with vibrant hues of red, orange, and purple as the light from the stars blends in fascinating ways. If one star is much brighter than the other, it might dominate the sky, while the dimmer star remains a beautiful complement. On the other hand, when one star sets, the remaining star would cast longer shadows and produce shifts in temperature, influencing the local climate and weather. The presence of two stars would also create interesting phenomena, such as varying durations of daylight and periods of twilight. Depending on the orientation of the planet's orbit and axial tilt, there could be times when one star is obscured or low on the horizon, creating dramatic contrasts in illumination. During eclipses caused by one star passing in front of the other, the sky could shift dramatically, plunging the environment into a darker, ethereal light that shapes the landscape in unique ways. Moreover, if the stars in a binary system are of different types, such as one being a red dwarf and the other a larger blue giant, the color contrast could be particularly striking. The atmospheric scattering of light may enhance these colors, leading to skies that are artistically painted with a range of shades throughout the day. For inhabitants of such a world, the experience of the sky would be filled with beautiful dynamics, influencing not just the environment, but also cultural expressions, myths, and meanings associated with their celestial neighbors. Detecting exoplanets that are too far away to see directly involves several sophisticated techniques, primarily relying on indirect observations. One of the most common methods is the transit method. This technique involves monitoring the brightness of a star over time. When a planet passes in front of its host star from our viewpoint, it blocks a small fraction of the star's light, causing a temporary dip in brightness. By measuring the size and duration of these dips, scientists can infer the planet's size, orbital period, and even its distance from the star. Another prominent method for detecting distant exoplanets is called radial velocity, or the Doppler method. As a planet orbits a star, it exerts a gravitational pull on the star, causing it to wobble slightly around a common center of mass. This wobble affects the star's spectrum, resulting in shifts in the wavelengths of light due to the Doppler effect. By analyzing these shifts, astronomers can determine the presence of a planet, its mass, and its orbit, even if the planet itself is not visible. Gravitational microlensing is another innovative technique utilized to detect exoplanets. This phenomenon occurs when the gravitational field of a star and any orbiting planets temporarily magnifies the light from a more distant star. If an exoplanet crosses the line of sight, the light curve will show specific patterns that indicate the presence of a planet. This method allows for the detection of planets that might not be located in the habitable zone or may be too faint to observe directly. Lastly, direct imaging can occasionally be employed to capture the light of exoplanets, but this is typically reserved for larger gas giant planets that are far from their host stars. Advanced telescope technologies such as coronagraphs or star shades can block out starlight, allowing observations of the dim light reflected from planets. As detection methods continue to improve, our understanding of exoplanetary systems expands, revealing more about the diversity of worlds beyond our solar system. The event horizon of a black hole is one of the most intriguing and enigmatic features in astrophysics. Essentially, it acts as a boundary that marks the point of no return. Once an object crosses this threshold, it cannot escape the gravitational pull of the black hole. The event horizon itself is not a physical surface, but rather a mathematical delineation, representing where the escape velocity exceeds the speed of light. Consequently, anything that ventures beyond this boundary is inexorably drawn inward, despite how fast it may be moving. As an object approaches the event horizon, several remarkable phenomena take place. The intense gravitational field distorts space and time, creating dramatic effects known as gravitational time dilation. For an observer far from the black hole, a clock falling into it would appear to tick more slowly as it nears the event horizon. This phenomenon leads to the perception that the object takes an infinite amount of time to actually cross the boundary, while for the object itself, it crosses without realizing it in finite time. An intriguing effect experienced near the event horizon is spaghettification. This term describes the extreme tidal forces experienced by an object due to the varying gravitational pull on different parts of it. For instance, if an astronaut were to fall feet first into a black hole, the gravitational force at their feet would be markedly stronger than at their head, stretching them elongated like a piece of spaghetti before ultimately becoming torn apart. Once an object crosses the event horizon, all information about it is seemingly lost to the outside universe, leading to one of the great debates in theoretical physics, the information paradox. According to quantum mechanics, information should not be lost. This conundrum invites a deeper exploration into the fundamental principles of gravity and quantum theory, indicating that our understanding of black holes and the nature of information in the universe is still evolving. The event horizon remains a gateway to some of the most profound mysteries of modern science. Supermassive black holes, which can possess millions to billions of times the mass of our Sun, are found at the centers of nearly all large galaxies, including our own Milky Way. Their formation is a complex process involving several stages that likely begins shortly after the Big Bang. Initially, small black holes formed from the collapse of massive stars in the early universe. These intermediate black holes, often dozens of times the mass of the Sun, began to populate the universe. Over time, these smaller black holes can merge with one another, forming increasingly larger black holes through a combination of gravitational attraction and gas accretion. As they accumulate mass, they can reach a tipping point, significantly increasing their gravitational influence. This process is greatly enhanced in the dense environments typically found in the centers of galaxies. In these regions, material such as gas and dust can easily be funneled toward the black hole, allowing it to grow rapidly through a process known as accretion. Another mechanism contributing to the formation of supermassive black holes involves the collapse of giant gas clouds. When these clouds condense under the force of gravity, they can directly form massive black holes without going through the intermediate stages. This direct formation could lead to significant masses very early in the universe's history, establishing supermassive black holes in the early galaxy formation. The interaction between supermassive black holes and their host galaxies also plays a critical role in their growth. The feedback from the black hole, such as energetic winds and jets, can influence star formation and the flow of gas within the galaxy, shaping its evolution. Observations suggest that as galaxies merge and interact, their central black holes can also coalesce, leading to the massive structures observed today. Overall, the formation of supermassive black holes is an intricate narrative that weaves together elements of star formation, gravitational dynamics, and cosmic evolution, demonstrating how central these colossal entities are to the very structure of the universe. Hawking radiation is a theoretical prediction made by physicist Stephen Hawking in 1974, describing the process through which black holes can lose mass and energy. According to quantum mechanics, empty space is not truly empty. It is teeming with virtual particle-antiparticle pairs that constantly pop in and out of existence. Near the event horizon of a black hole, these particle pairs can have intriguing fates. When a particle-antiparticle pair forms just at the event horizon, one particle might fall into the black hole while the other escapes into space. The escaping particle becomes known as Hawking radiation. Since the particle that enters the black hole carries negative energy, the black hole effectively loses a tiny amount of its total mass. This process is gradual and incredibly slow for large black holes, as the energy lost is minuscule compared to the mass of the black hole itself. As Hawking radiation continues over vast periods, it causes the black hole to lose mass and slowly evaporate. For stellar mass black holes, the evaporation process is so gradual that it would take billions of years to notice any significant changes. However, for smaller primordial black holes, which may have formed in the early universe, evaporation could occur on a shorter timescale, potentially leading to the complete dissipation of these black holes. This concept introduces some thought-provoking implications for black hole physics and the ultimate fate of these mysterious objects. The idea that black holes can evaporate presents a challenge to our understanding of information, as it raises questions about what happens to the information that falls into a black hole. This dilemma, known as the information paradox, continues to inspire debates and research in theoretical physics, highlighting the complex interplay between quantum mechanics and general relativity. Hawking radiation emphasizes that black holes are not immutable, they evolve, leading to new insights into the fundamental nature of the universe. White holes are fascinating theoretical constructs that emerge from the equations of general relativity, acting as the opposite of black holes. While black holes draw in matter and light, resulting in a region from which nothing can escape, a white hole is theorized to expel matter and prevent anything from entering. Essentially, if black holes trap anything that crosses their event horizons, white holes would do the exact opposite, spewing out energy and particles. The concept of white holes arises from certain solutions to Einstein's field equations, particularly those related to the Schwarzschild metric and its extensions. They are often depicted as existing at the end of a black hole's event horizon, suggesting a connection to a separate region of space-time. This leads to intriguing possibilities, such as the idea that matter entering a black hole could emerge from a white hole in another part of the universe, or even in another universe altogether. Such scenarios fuel speculative discussions about wormholes, which might serve as bridges between disparate regions of space and time. However, despite their intriguing theoretical foundation, there is currently no observational evidence for the existence of white holes. Their stability is also questionable, as any mass expelled by a white hole would likely interact with surrounding matter, making the persistence of a white hole problematic. Additionally, a white hole's characteristics suggest it should be fundamentally different from the behavior of black holes, complicating the concept of causality in physics. The intriguing nature of white holes raises questions about the fundamental principles of physics and the nature of space-time. While they can spark the imagination and contribute to discussions around the universe's mysteries, their actual existence remains in the domain of theoretical exploration rather than empirical observation. As our understanding of the cosmos expands, the nature and potential implications of such exotic objects continue to inspire both scientists and enthusiasts alike. Falling into a black hole would lead to a series of extraordinary and ultimately catastrophic experiences, heavily shaped by the black hole's characteristics and the laws of physics. Initially, as you approached the black hole, you would experience an overwhelming increase in gravitational pull. This is particularly pronounced for smaller black holes, where strong gravitational gradients create a phenomenon known as spaghettification. As you got closer, the difference in gravitational force between your head and feet would stretch you out in a process akin to being pulled into a long, thin shape, similar to spaghetti. As you crossed the event horizon, the boundary beyond which nothing can escape the black hole's gravity, the experience of time would begin to distort dramatically. From an outside observer's perspective, it would seem as though you were moving slower as you approached the event horizon due to gravitational time dilation. Your image would fade and become increasingly redshifted, almost as if stuck in perpetual twilight. Conversely, from your perspective, the crossing would occur without any noticeable event. You would not even realize you had crossed until it was too late. Once inside the event horizon, all paths lead irreversibly toward the singularity at the black hole's core. This singularity is a point where gravitational forces compress matter to an infinitely small volume, creating the most extreme conditions in the universe. The laws of physics as we understand them break down at this point, and any matter, including you, would be crushed to an infinitely dense state. The exact nature of what happens within the singularity is still a mystery, as our current understanding of physics cannot describe the behavior of matter in such extreme conditions. While the thought of falling into a black hole paints an unsettling picture, it also illustrates profound concepts in gravitational theory and quantum mechanics. Such an encounter invites deeper questions about the nature of reality, the fabric of space-time, and the fundamental forces governing the universe. It also highlights the awe-inspiring yet terrifying world that lies beyond our observable limits, stimulating scientific inquiry and philosophical debates alike. Binary black hole systems, which consist of two black holes orbiting each other, exhibit fascinating dynamics governed by their gravitational interactions. As these black holes orbit, they create strong gravitational waves, ripples in space-time that can propagate across vast distances. The strength of these gravitational waves increases as the black holes spiral closer together, especially when they are on the brink of merging. The detection of such waves is significant, as it provides direct evidence for the existence of black holes and opens a new window for understanding the universe. The behavior of binary black holes is influenced by their masses and the distance between them. As they orbit, they lose energy through the emission of gravitational waves, which causes them to gradually move closer together over time. This loss of energy leads to an acceleration of their orbital frequency, bringing them into a tighter and faster orbit. As they get closer, the process can become increasingly rapid, culminating in a merger where the two black holes combine into a single, more massive black hole. During a merger, the resulting gravitational waves produce distinctive signals known as chirps. These signals are characterized by a frequency increase followed by a sudden drop, reflecting the final moments before the black holes collide. Advanced observatories like LIGO and Virgo have successfully detected these chirps, allowing scientists to catalog various binary black hole mergers. This not only provides insight into the populations of black holes in the universe, but also contributes to our understanding of their formation and evolution. The aftermath of a merger can be equally dramatic. The newly formed black hole may initially be in an excited state, emitting strong gravitational waves before settling into a stable configuration. The merger process can also lead to the ejection of matter and energy, offering clues about how black holes interact with their environments. Studying binary black hole systems enhances our grasp of general relativity and highlights the intricate dance of these enigmatic objects, revealing deeper truths about the nature of gravity, space-time, and the cosmos itself. Quasars are among the most luminous objects in the universe, often outshining entire galaxies. Their incredible brightness is intrinsically linked to supermassive black holes which reside at their centers. A quasar is essentially a type of active galactic nucleus, where a supermassive black hole is actively accreting material from the surrounding environment. This process generates immense amounts of energy, primarily in the form of electromagnetic radiation, including visible light, radio waves, and X-rays. As matter spirals toward the supermassive black hole, it forms an accretion disk, a rotating disk of gas and dust heated to extreme temperatures due to friction and gravitational forces. This disk emits radiation as the material is accelerated and compressed. The energy produced can be several orders of magnitude greater than that emitted by all the stars in a galaxy combined, making quasars detectable from billions of light years away. The intense emissions allow astronomers to observe these distant objects and gain insights into the early universe. The connection between quasars and supermassive black holes also extends to their growth and evolution. Supermassive black holes are thought to have formed in the early universe, rapidly gaining mass by accreting gas and merging with other black holes. During this phase, they would become quasars, marking a period of high activity and brightness. Understanding how and when these supermassive black holes turned into quasars provides valuable insights into the formation of galaxies and the evolution of structures in the universe. Additionally, the properties of quasars can help us explore cosmic distances and the expansion of the universe. Observations of quasars across different redshifts allow astronomers to gather information about the conditions of the early universe, shedding light on the interplay between black holes and their host galaxies. The study of quasars not only deepens our understanding of supermassive black holes, but also highlights their significant role in cosmic evolution. Detecting black holes is indeed a complex challenge, primarily because they do not emit light and therefore cannot be seen directly. However, astronomers have developed several indirect methods to identify their presence and infer their characteristics. One of the most common techniques relies on observing the effects of a black hole's immense gravitational pull on nearby stars and gas. When a black hole is part of a binary system, or when it is in close proximity to other stars, its gravitational influence can be observed. Scientists can track the motion of nearby stars and gas clouds, noting how they orbit around an unseen mass. By applying Newtonian physics or general relativity to the movements of these objects, researchers can deduce the mass of the black hole, even if it remains invisible. This method has led to the identification of numerous black holes, including the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. Another avenue for detection comes from the observation of X-ray emissions that arise when matter is drawn toward a black hole, forming an accretion disk. As gas and dust spiral into the black hole, they heat up due to friction and extreme gravitational forces, emitting X-rays in the process. Researchers utilize X-ray telescopes to explore these emissions, revealing the presence of black holes, especially those that are actively accreting material. Gravitational waves present yet another groundbreaking method for detecting black holes. When two black holes collide, they produce ripples in space-time that can be detected by observatories like LIGO and Virgo. These gravitational waves carry information about the masses and spins of the merging black holes, allowing scientists to study events that occurred far away and long ago. Overall, the combination of tracking stellar movements, detecting X-ray emissions, and observing gravitational waves has revolutionized our ability to study black holes. These indirect methods have not only confirmed the existence of black holes, but also expanded our understanding of their properties, formation, and the role they play in galaxy formation and evolution. Intermediate mass black holes are an intriguing and somewhat mysterious class of black holes that possess masses ranging from hundreds to tens of thousands of times that of our Sun. They sit between stellar black holes, which form from the collapse of massive stars, and supermassive black holes, found at the centers of galaxies. Despite being theorized for decades, intermediate mass black holes remain elusive and challenging to detect, presenting a puzzle for astrophysicists. One of the primary reasons for the difficulty in identifying intermediate mass black holes lies in their formation process. While stellar black holes are relatively common and well understood, formed from the remains of massive stars after they exhaust their nuclear fuel, the origins of intermediate mass black holes are still a matter of active research. They may form through the merging of smaller black holes within dense star clusters, or through the collapse of very massive star clusters. Understanding these processes is crucial for distinguishing them from their more massive and lighter counterparts. Additionally, the observational signatures of intermediate mass black holes are subtle. They do not typically produce the strong X-ray emissions associated with active accretion like supermassive black holes do. Instead, they may appear as the gravitational influences on their surroundings, such as stars or gas clouds, making their detection akin to looking for shadows rather than direct light. Their low luminosity and the fact that they are often located far from the centers of galaxies complicate efforts to identify them through traditional methods. Recent advances in technology and observational techniques, however, are bringing new hope in the search for these elusive black holes. Researchers are increasingly utilizing gravitational wave detections from merging black holes, which could uncover the existence of intermediate mass black holes as they collide and form higher mass objects. Observations of star clusters and regions where interactions between stars are intense may also lead to the discovery of these intriguing entities. Understanding intermediate mass black holes is essential, as they could provide insights into the evolution of black holes and the formation mechanisms that bridge the gap between stellar and supermassive varieties. Primordial black holes, which are theorized to have formed in the chaotic conditions of the early universe, could indeed still exist today. These black holes are thought to have originated within the first few moments after the Big Bang, during a period of rapid expansion. Unlike the black holes we observe forming from collapsing stars, primordial black holes emerge from density fluctuations in the fabric of space-time itself. Researchers estimate that if these black holes were sufficiently small, perhaps weighing less than about 100,000 times the mass of the Sun, they could have evaporated over time due to a process known as Hawking radiation. This theoretical radiation predicts that black holes emit energy and can ultimately lose mass until they disappear completely. However, larger primordial black holes, which might be several times the mass of the Sun, can continue to exist and could be a significant component of the universe's dark matter. While evidence for primordial black holes remains elusive, scientists continue to search for them through various observational strategies. For example, researchers have looked for signs of these black holes interacting with normal matter, or influencing gravitational waves produced by colliding objects in space. If confirmed, the existence of primordial black holes could provide crucial insights into the conditions of the early universe and deepen our understanding of cosmic evolution. The idea that these ancient black holes might still be lingering in the universe is fascinating. They represent a unique connection to the universe's infancy, inviting curiosity about how they shaped the cosmic landscape we see today. As we gather more data and refine our theories, the enigma of primordial black holes may unlock new chapters in our comprehension of the cosmos. The Great Attractor is a vast gravitational anomaly located in the vicinity of the Milky Way galaxy, situated about 100 million light-years away in the direction of the Centaurus constellation. It represents a region where a significant amount of mass, including galaxies and clusters of galaxies, appears to be pulling nearby structures towards it. This gravitational influence is so strong that it affects the motion of galaxies across an extensive area of the universe. The exact nature of the Great Attractor remains somewhat mysterious, primarily because it sits behind the dense plane of our own galaxy, obscuring direct observations. However, it is believed to harbor a substantial concentration of mass, likely composed of dark matter along with numerous galaxy clusters. This gravitational pull is responsible for the observed motion of our own Milky Way and many other galaxies that fall within this region. These galaxies are collectively drifting toward the center of this massive concentration of matter, highlighting the complex interplay of gravitational forces at play in the cosmos. Scientists have identified several galaxy clusters that appear to contribute to the Great Attractor's gravitational field. Among them is the Norma cluster, which is one of the more massive clusters in that region. As the galaxy clusters interact with one another and the surrounding dark matter, the combined gravitational effect draws an array of galaxies toward this central mass, creating a fascinating dynamic. The Great Attractor challenges our understanding of cosmic structures and their interactions. It underscores the importance of gravitational forces in shaping the distribution and motion of galaxies across the universe. By studying such anomalies, astronomers can gain deeper insights into the overall structure of the universe, the distribution of dark matter, and the forces that govern galactic motion on a grand scale. Cosmic voids are vast, empty regions of space that exist between galaxies and galaxy clusters. These voids represent some of the largest structures in the universe, often spanning tens to hundreds of millions of light-years across. Their formation is closely tied to the evolution of the universe and the distribution of matter over time. Initially, in the early universe, matter was distributed somewhat uniformly. However, as the universe expanded and cooled, slight fluctuations in density began to develop. Over billions of years, regions of higher density attracted more matter due to gravitational forces, leading to the formation of galaxies and clusters. Conversely, regions of lower density, where matter was thinly spread, continued to expand, creating the large voids we see today. The interplay between gravity and cosmic expansion effectively carved out these empty spaces in a process that is still ongoing. As galaxies cluster together due to gravity, voids emerge where the gravitational pull is weaker, resulting in vast expanses with significantly fewer galaxies than surrounding areas. Inside these cosmic voids, the environment is remarkably different from that of dense clusters. While you might expect them to be completely empty, they are not devoid of matter altogether. Cosmic voids can contain a sparse population of galaxies, dark matter, and gas. The galaxies found within these areas tend to be less numerous and less massive compared to those in denser regions. Additionally, voids can harbor intergalactic gas and dark matter, contributing to the intricate web of the universe's structure. Studying cosmic voids offers valuable insights into the overall dynamics of the universe. They play a crucial role in understanding dark energy, gravitational interactions, and the large-scale structure of cosmic formations. The properties of voids, including their sizes and shapes, provide observational clues about the history of the universe's expansion and the nature of the forces that have shaped it into what we see today. The filamentary structure of the cosmic web arises from the gravitational interactions between galaxies, dark matter, and gas over vast scales. This web-like arrangement is a consequence of the universe's expansion and the initial density fluctuations that occurred shortly after the Big Bang. As the universe grew and cooled, regions with slightly higher density gradually attracted surrounding matter, establishing a network of threads that extends across cosmic distances. These filaments are primarily composed of dark matter which does not emit light and is therefore invisible to conventional observations. The gravitational influence of dark matter causes visible matter, such as galaxies and gas, to congregate along these filaments. This results in the formation of interconnected structures where galaxies are found predominantly within the denser regions of the filaments and clusters, while voids exist in between. The distribution of galaxies reflects the underlying dark matter network, creating the characteristic web-like appearance. The interplay of gravity and cosmic expansion plays a fundamental role in determining the shapes and sizes of these filaments. As matter is attracted to the denser regions, it leads to the continuous growth of these structures. Over billions of years, the cosmic web has evolved, causing the filaments to stretch and evolve as they interact with one another and the expanding universe. This dynamic process results in a complex tapestry of interconnected structures that showcases how gravitational forces shape the universe on the largest scales. Studying the filamentary structure of the cosmic web provides critical insights into the nature of dark matter and the overall evolution of the universe. Mapping these filaments helps astronomers understand the distribution of galaxies and the underlying physical processes driving cosmic growth. By observing how filaments interact with galaxies and clusters, scientists can gain deeper knowledge of the fundamental forces governing the universe's architecture. Galaxy clusters, the largest gravitationally bound structures in the universe, interact with one another in several fascinating ways, primarily through gravitational attraction. As these massive clusters form from the accumulation of smaller groups of galaxies, they begin to influence each other's growth and evolution. The gravitational forces between galaxy clusters can lead to a variety of interactions, including mergers, tidal forces, and the creation of large-scale structures like superclusters. When two galaxy clusters collide, the interaction can be extremely energetic. As they approach each other, their constituent galaxies often pass by one another without significant direct impacts due to the vast distances between them. However, the hot gas surrounding the galaxies can collide, resulting in shock waves and the emission of X-rays. This interaction can also lead to the merging of the clusters, a process that can take hundreds of millions of years, allowing them to form even larger clusters. These mergers can drastically change the characteristics of the clusters involved, affecting their dynamics and triggering bursts of star formation. In addition to collisions and mergers, galaxy clusters can exert tidal forces on each other. These forces can lead to the stretching and distortion of the clusters, affecting the distribution of galaxies and gas within them. Tidal interactions can also strip away galaxies or gas from one cluster to another, a phenomenon known as galaxy harassment. These interactions can even cause galaxies to change their orbits, influencing their future trajectories and relationships with neighboring clusters. The study of these interactions is crucial for understanding the universe's large-scale structure and the dynamics of galaxy evolution. Observations of various clusters provide significant insights into the properties of dark matter, the nature of intergalactic gas, and the overall behavior of cosmic structures. By examining the complex relationships between galaxy clusters, scientists can better comprehend the processes that drive cosmic evolution and shape the universe we observe today. The largest known structures in the universe are colossal cosmic formations that include galaxy superclusters, great walls, and voids, which are interconnected into a vast network often referred to as the cosmic web. One of the most prominent examples is the Sloan Great Wall, a massive galaxy supercluster that spans approximately 100 million light-years across. This enormous structure consists of numerous galaxies and galaxy clusters, showcasing how matter is organized on the grandest scales. Another significant structure is the Hercules Corona Borealis Great Wall, which is considered one of the largest known structures in the universe. It measures around 10 billion light-years in length, making it a colossal grouping of galaxies, clusters, and superclusters tied together by gravitational forces. Its discovery has profound implications for our understanding of the universe, as it challenges the traditional views of homogeneity and isotropy on large scales, suggesting that the universe might be more complex than previously thought. In addition to these superclusters, voids also play a crucial role in the landscape of large-scale structures. Cosmic voids are vast, empty regions of space that can stretch for hundreds of millions of light-years. They serve as the gaps between the dense filaments of galaxies and clusters, highlighting the incredible diversity of structures throughout the cosmos. While they may appear empty, these regions contain dark matter and a sparse population of galaxies, offering a fascinating counterpoint to the dense areas of the universe. Exploring these immense structures helps scientists learn about cosmic evolution, the distribution of dark matter, and the dynamics governing galaxy formation and interaction. The relationships between superclusters and voids within the cosmic web reveal the fundamental architecture of the universe and continue to deepen our understanding of its history and development on the largest scales. Galaxies evolve over time through a combination of processes that involve gravitational interactions, star formation, gas dynamics, and merging events. Initially, galaxies began to form in the early universe from fluctuations in density, where regions of gas and dark matter began collapsing under their own gravity. This led to the birth of the first stars, which ignited the transformation of simple gas clouds into complex structures. As galaxies grow, they experience significant changes in their morphology and star populations. During their evolution, galaxies can collide and merge with one another, a process that can dramatically alter their size and shape. Major mergers, where two large galaxies combine, can trigger intense periods of star formation as gas is funneled toward the galactic center, sometimes leading to the creation of elliptical galaxies. These interactions can also redistribute stars, gas, and dark matter, reshaping the galaxy's structure and dynamics. The star formation rate within a galaxy is a crucial aspect of its evolution. Initially, many galaxies experience high rates of star formation, culminating in a vibrant and active cosmic environment. However, as gas is consumed in star formation and galaxies exhaust their available star-forming material, the rates may decline. This process can result in what is termed a quenching of star formation, leading to older populations of stars and eventually transforming the galaxy into a more passive, red, and dead system. Over very long timescales, galaxies continue to evolve by shedding and acquiring material through various mechanisms. They can gain gas and dust from their surroundings or through interactions with smaller dwarf galaxies. Moreover, the complex interplay of gravitational forces among galaxies leads to the ongoing transformation of the cosmic landscape. Understanding these processes not only reveals the history of individual galaxies, but also sheds light on the larger narrative of galaxy formation and evolution throughout the cosmic timeline. Magnetic fields play a significant and often underappreciated role in shaping cosmic structures throughout the universe. These fields are present in various astrophysical environments, including galaxies, galaxy clusters, and intergalactic space. Their influence can be seen on a range of scales, impacting gas dynamics, star formation, and the overall structure of galaxies. In galaxies, magnetic fields are intertwined with the interstellar medium, the gas and dust that fill the spaces between stars. These fields can influence the motion of charged particles within the gas, helping to regulate the flow of material and affecting the process of star formation. For example, magnetic fields can provide additional pressure that supports regions of gas against gravitational collapse, thereby controlling the birth of new stars. They can also contribute to the turbulence within the gas, impacting how efficiently material flows into star-forming regions. On larger scales, magnetic fields play a role in the behavior of galaxy clusters and cosmic filaments. When clusters collide or interact, magnetic fields can affect the dynamics of the hot gas that fills these structures. This interaction can lead to the formation of shock waves and complex patterns of gas flow, influencing the distribution of matter within the cluster. In the cosmic web, magnetic fields are thought to contribute to the gas dynamics within filaments, potentially impacting how galaxies are distributed along these structures. Understanding the role of magnetic fields in cosmic structures is essential for developing a comprehensive picture of astrophysical processes. Observations of magnetic fields, often measured through their effects on polarized light from distant galaxies, provide clues about their strengths and configurations. These studies not only enhance our understanding of galaxy formation and evolution, but also reveal the underlying physics that governs structure in the universe on the largest scales, highlighting the intricate interconnections between magnetic phenomena and cosmic developments. Mapping the distribution of dark matter in the universe is a complex but essential task for understanding its role in cosmic structure formation. Despite being invisible and not interacting with light, dark matter can be inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Several methods are employed by astronomers to create these maps. One of the primary techniques is gravitational lensing, which occurs when massive objects like galaxy clusters bend the light from more distant galaxies. This effect can magnify and distort the images of those distant galaxies. By analyzing these distortions, scientists can infer the presence and distribution of dark matter within the foreground clusters. The degree of bending reflects the mass of the lensing object, allowing researchers to map the concentration of dark matter associated with it. This method has proven especially useful on large scales, as it provides insights into the massive structures of the universe. Another approach relies on observing the motions of galaxies within clusters. By measuring their velocities, astronomers can assess the gravitational pull exerted on them, revealing the total mass of the cluster, including the dark matter component. This technique, known as dynamical studies, helps scientists estimate dark matter's distribution around galaxy clusters and is often combined with other observations for more accurate results. Additionally, the cosmic microwave background radiation offers insights into the early universe's matter distribution. By studying tiny fluctuations in temperature across the CMB, scientists can infer the density variations that led to the large-scale structure we see today. These fluctuations, tied to the presence of both visible matter and dark matter, help map out the web-like pattern where dark matter congregates. Through these combined techniques, astronomers continuously refine their understanding of dark matter's distribution throughout the universe. This ongoing research is crucial for piecing together the nature of dark matter, its interactions, and its influence on the formation and evolution of galaxies and larger structures. Insights gained from mapping dark matter contribute significantly to our broader understanding of the universe and its mysterious components. The rotation of galaxies often appears to be faster than predicted by the amount of visible matter they contain. This discrepancy is most clearly observed in spiral galaxies, where the outer regions rotate at unexpectedly high speeds. According to Newtonian mechanics and the visible mass from stars and gas, the velocity of stars should decrease with distance from the galactic center, much like the planets in our solar system. However, observations reveal that stars in the outer edges of galaxies orbit at similar or even faster speeds than those close to the center, creating what is known as the galaxy rotation problem. The most widely accepted explanation for this phenomenon is the presence of dark matter. Dark matter is a mysterious and invisible component that does not emit or absorb light, making it undetectable through standard observational methods. However, it exerts a significant gravitational influence, contributing to the overall mass of galaxies. It is believed to form a halo around galaxies, providing the extra gravitational pull necessary to explain the faster-than-expected rotation rates. This dark matter halo extends well beyond the visible edges of galaxies, which accounts for the higher orbital speeds seen in peripheral regions. Numerous studies have gone into mapping the distribution of dark matter in galaxies and galaxy clusters, further supporting this hypothesis. For example, by examining the behavior of objects in different parts of a galaxy, astronomers can infer the gravitational effects of dark matter and understand its concentration. The presence of dark matter also influences how galaxies interact with one another, affecting merger rates and the overall dynamics within cosmic structures. While dark matter serves as the leading explanation for the rapid galactic rotation problem, research continues into alternative theories, such as modifications to the laws of gravity. Future observations and experiments will further test these ideas and enhance our understanding of the fundamental nature of galaxies and the universe itself. Exploring these dynamics not only reveals the behaviors of galaxies, but also leads to deeper insights into the components that govern cosmic structures. Galactic superclusters are massive groups of galaxy clusters and groups that form the largest known structures in the universe. Their formation begins in the early universe, shortly after the Big Bang, during a time when fluctuations in density were present in the primordial soup of particles. As the universe expanded and cooled, regions with slightly higher densities began to collapse under their own gravity, leading to the earliest galaxy formation. Over time, these galaxies began to cluster together as gravitational forces pulled them closer. The evolution of superclusters is intricately linked to the dynamics of dark matter and baryonic matter, which includes ordinary matter like stars, gas, and dust. Dark matter plays a fundamental role by providing the necessary gravitational scaffolding. As dark matter halos form, they attract visible matter and other dark matter, aiding in the assembly of cosmic structures. Various processes, such as merging smaller clusters and the ongoing accretion of gas and galaxies, contribute to the growth of superclusters over billions of years. Galactic interactions are also vital to the evolution of superclusters. When individual galaxy clusters collide or merge, they can trigger bursts of star formation and redistribute their constituent galaxies. This merging process leads to larger and richer superclusters, as well as changes in the types of galaxies within them. For instance, as galaxies collide, they can reshape their morphology, leading to the formation of elliptical galaxies from spiral galaxies, and altering the overall diversity of the cluster's population. The environments within superclusters can also vary significantly, influencing the properties of the galaxies residing there. The dense regions of a supercluster may be characterized by active star formation and interactions, while the outskirts typically exhibit a more relaxed environment with fewer active processes. Studying the formation and evolution of superclusters provides astronomers with essential insights into the cosmic web structure and the large-scale dynamics that shape the universe. These insights continue to refine our understanding of cosmic evolution and the interplay between dark matter, baryonic matter, and the forces that govern galaxy formation. The pulsation of some stars is a fascinating phenomenon, attributed primarily to variations in their internal structure and energy balance. Stars that exhibit pulsations are often classified as variable stars. The pulsation is usually a result of thermal instability in their outer layers, which leads to periodic expansions and contractions. This process typically occurs in specific types of stars, such as Cepheid variables and RR Lyrae stars, each with distinct characteristics. One common cause of pulsation is the process of stellar oscillation. In stars like Cepheid variables, these oscillations are driven by the balance between radiation pressure and gravitational forces. When the star's outer layers heat up and expand, the pressure increases, leading to a temporary instability. As the star expands, it cools and contracts under the influence of gravity. This cycle of expansion and contraction occurs periodically, resulting in noticeable changes in brightness over time. Another mechanism behind pulsation involves the Kappa mechanism, which is particularly relevant in massive stars. In this scenario, elements like helium and hydrogen undergo ionization at different layers within the star. When the outer layers are heated, the opacity of the material changes, affecting how energy radiates away from the star's interior. This change in opacity can create a feedback loop, causing the star to expand and contract. These changes lead to periodic variations in brightness, and depending on the specific conditions and the star's mass, this can induce different types of pulsations. The study of pulsating stars is not only intriguing from a stellar evolution standpoint, but it also holds significant observational implications. For instance, The regularity of pulsations in Cepheid variables has made them crucial as standard candles in measuring astronomical distances. By understanding the mechanisms behind stellar pulsations, astronomers can glean insights into stellar interiors, stellar evolution, and even gain a deeper understanding of the cosmos. Magnetars are a type of neutron star characterized by their extraordinarily strong magnetic fields, which can be over 1,000 times more powerful than those of typical neutron stars and significantly stronger than any magnetic fields produced by celestial objects. The formation of these incredibly strong magnetic fields is primarily attributed to the processes that occur during the birth and evolution of neutron stars. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, leading to the collapse of its core into a neutron star. During this collapse, the star's core compresses dramatically, and conservation of angular momentum causes it to spin faster. This intense compression can amplify any pre-existing magnetic field, resulting in a strong magnetic field as the star becomes a neutron star. Some theories suggest that the magnetic field is further intensified due to the rapid rotation and the complex inner structure of neutron stars, which includes superconducting materials. Once formed, the magnetic fields of magnetars can become even stronger through a process called magnetic flux emergence. As the neutron star undergoes cooling and evolving dynamics, the magnetic field lines can become distorted and compressed. This mechanism can create very high magnetic field strengths, especially in the case of magnetars, where the field can reach magnitudes of about 1 quadrillion Gauss, far beyond typical astronomical values. Additionally, magnetars are known to produce intense bursts of electromagnetic radiation, including X-rays and gamma rays, which can be linked to their magnetic fields. The energy associated with the magnetic field is released in the form of bursts when the magnetic field lines reconnect and realign, leading to the release of immense energy. Understanding the formation and properties of magnetars helps provide deeper insights into the complex interplay of gravity, nuclear physics, and magnetic forces operating in extreme environments. These enigmatic objects serve as natural laboratories for studying matter under conditions that cannot be replicated on Earth, enriching our overall understanding of fundamental astrophysical processes. A gamma-ray burst is an extraordinarily energetic explosion that occurs in distant galaxies, producing intense gamma-ray radiation. These bursts are among the most powerful events in the universe, capable of releasing more energy in a few seconds than the Sun will emit over its entire lifetime. Gamma-ray bursts are typically divided into two categories: short bursts and long bursts, each linked to different astronomical phenomena. Long gamma-ray bursts lasting from several seconds to several minutes are believed to be associated with the death of massive stars. When a massive star exhausts its nuclear fuel, it can undergo a core collapse, leading to the formation of a black hole or a neutron star. The core collapse releases an enormous amount of energy, creating jets of high-energy particles that shoot out at nearly the speed of light. As these jets interact with the star's outer layers, they produce intense gamma radiation. The resulting explosion is observed as a long gamma-ray burst, often accompanied by a supernova. Short gamma-ray bursts, lasting less than 2 seconds, are thought to originate from the merger of compact objects like neutron stars or black holes. When these dense companions collide, they create a violent explosion that emits a burst of gamma rays. The energy released during these mergers can lead to the formation of heavier elements, such as gold and platinum, through rapid neutron capture processes. This synthesis contributes to the enrichment of the universe with heavy elements. Gamma-ray bursts are detectable across vast cosmic distances, and their light can be observed by instruments on space-based observatories. Following the initial burst, afterglows in the X-ray, optical, and radio wavelengths are often observed, providing valuable information about the distance, location, and properties of the host galaxy. This study helps astronomers understand the conditions under which these bursts occur and the processes that govern their production. The study of gamma-ray bursts provides profound insights into the life cycles of stars, the nature of black holes, and the synthesis of elements in the universe. By observing and analyzing these incredible phenomena, astronomers continue to explore the fundamental workings of the cosmos and the extreme environments that give rise to such dramatic events. Heavy elements are formed in neutron-star collisions through a process known as rapid neutron capture, or the R process. When two neutron stars collide, they create a highly energetic environment that is rich in neutrons. This collision occurs when two neutron stars in a binary system spiral inward and finally merge, leading to an explosion that releases enormous amounts of energy and a flood of neutrons. During the merger, the intense conditions produce neutron-rich material, allowing for rapid neutron capture to take place. In this environment, atomic nuclei can absorb neutrons much more quickly than they can undergo beta decay, a process that transforms neutrons into protons. As the merging neutron stars eject neutron-rich material into space, the newly formed atomic nuclei rapidly capture additional neutrons, creating increasingly heavy isotopes. Once the supply of neutrons begins to dwindle, some of these heavy nuclei undergo beta decay, converting some of their neutrons into protons and resulting in the formation of heavier elements. This explosive environment is essential for synthesizing many of the universe's heavy elements, including gold, platinum, and uranium. Observations of the gravitational waves produced by neutron star mergers, along with the electromagnetic radiation following the event, indicate the presence of these heavy elements in the aftermath of such collisions. In particular, researchers have detected signatures of heavy elements formed during a neutron star merger, such as those observed in the aftermath of the merger event GW-117, which was detected in 2017. The synthesis of heavy elements during neutron star collisions highlights the crucial role these events play in enriching the universe with the building blocks of planets and life. By studying these processes, astronomers continue to deepen our understanding of nucleosynthesis and the evolution of elements in the cosmos. The study of neutron star mergers not only sheds light on the origins of heavy elements, but also opens up new perspectives on the fundamental physics governing extreme astrophysical environments. Tabby's star, officially known as KIC 847-220, has intrigued astronomers due to its unusual dimming patterns. Observations show that this star experiences irregular dips in brightness, which has led to a range of theories and much speculation. The intensity of these dimming events has been so pronounced that it has fostered wild ideas, including the possibility of an alien megastructure orbiting the star, although that is not the leading explanation among scientists. One of the more plausible theories involves the presence of a large cloud of dust orbiting around Tabby's star. This dust could absorb and scatter light in ways that result in the observed brightness variations. Such clouds might be remnants from a collision of celestial bodies or from the star's own material being shed. Unlike planets, which may cause periodic transits and more predictable dimming, the cloud-based scenario suggests a more chaotic pattern, which aligns with the erratic behavior we observe. Another consideration is the possibility of the star itself undergoing variations in its output. Just as our sun exhibits changes in brightness due to solar flares and sunspots, Tabby's star might have its own internal processes that lead to fluctuating luminosity. However, the scale and pattern of the dimming observed are unlike what has been documented in typical stars. The deduction of the causes behind Tabby's star continues to be a subject of active research. Each passing observation adds layers to our understanding, and as new technologies enhance our capacity for stellar study, we may eventually uncover the rationale behind this cosmic enigma. Until definitive answers arise, Tabby's star remains a captivating mystery in our celestial neighborhood, prompting scientists to rethink their understanding of stellar behavior. Binary star systems consist of two stars orbiting a common center of mass, and their dynamics can significantly influence the formation and evolution of surrounding planetary systems. The presence of another star creates a complex gravitational environment which can alter the typical processes involved in planetary formation that usually occur around a solitary star. As a result, the conditions in binary systems are often distinct, affecting every phase, from the initial gas and dust cloud to the development of planets. During the early stages of a binary star system, the gravitational interactions between the two stars can lead to instability in the surrounding accretion disk, which is a collection of gas and dust that provides the material necessary for planet formation. Instead of a stable environment enabling planets to form in a predictable manner, we find that the gravitational pull of one star can cause the disk to become elongated or fragmented, creating conditions conducive to both the development of planets and the potential ejection of material from the system altogether. Planetary orbits in binary systems can also be influenced by the presence and proximity of the second star. Depending on the distance between the two stars, planets may either orbit around just one of the stars or be captured into a more complex orbit that takes them around both stars. This can lead to a variety of orbital configurations, some of which may not support the long-term stability necessary for planets to retain their atmospheres or sustain life. Interestingly, many binary systems have been discovered that harbor planets, demonstrating that planetary formation can still occur under these challenging gravitational circumstances. This diversity in planetary environments prompted by binary stars helps us expand our understanding of how multiple star systems function and how they might contribute to the overall diversity of planetary systems observed throughout the universe. The interplay of these forces offers ongoing intrigue as scientists seek to learn more about the rich complexities of the cosmos. The life cycle of a star unfolds in a series of distinct stages, each characterized by unique processes governed by the laws of physics, particularly nuclear fusion. This journey begins in a cold, dense region of a molecular cloud where gas and dust gather to form a protostar. Gravity pulls the material together, causing the temperature and pressure at the core to rise. Eventually, once conditions are right, nuclear fusion ignites, marking the birth of a new star as it converts hydrogen into helium, releasing energy in the process. Once a star enters the main sequence phase, it remains in this stable period for the majority of its life, often spanning billions of years. This is the stage during which stars, like our Sun, maintain a delicate balance between the gravitational collapse inward and the outward pressure from nuclear fusion. Over time, as the hydrogen fuel in the core depletes, the star begins to evolve, leading it into the next stages of its life cycle. For stars similar to the Sun, once the hydrogen is exhausted, they transition into red giants. Here, the core contracts and the outer layers expand and cool, giving the star its reddish hue. Fusion processes shift to heavier elements, as the star starts to fuse helium into carbon and oxygen. Eventually, the outer layers will be expelled, creating a beautiful planetary nebula, while the core remains as a white dwarf, a dense remnant that will cool over time. More massive stars have a more dramatic fate. After becoming red supergiants, these stars can undergo a series of fusion processes, forming heavier elements until they eventually reach iron, which cannot release energy through fusion. This leads to an unstable core that eventually collapses, culminating in a cataclysmic supernova explosion. What remains can be a neutron star, or, if massive enough, a black hole, marking the end of a grand stellar life while seeding the universe with heavy elements essential for new stars and planets. The entire cycle highlights the exquisite balance of forces and stellar processes that shape the cosmos. The idea of a star surviving a supernova explosion may seem paradoxical, given that a supernova is typically the end of a star's life cycle. However, the term surviving refers to what happens to the remnants of a star and how certain astronomical entities can emerge from the explosion rather than the star itself continuing to exist in its original form. Specifically, this phenomenon often involves massive stars that reach the end of their nuclear fusion processes. When a massive star runs out of nuclear fuel, its core collapses under the force of gravity. This collapse generates an enormous amount of energy that leads to the outer layers of the star being expelled in a spectacular explosion known as a supernova. The core, however, does not simply vanish, it can become a neutron star, or in cases of particularly massive stars, a black hole. These remnants represent the core surviving the supernova explosion, albeit in a drastically altered state. Neutron stars are incredibly dense remnants that result when the core's protons and electrons combine to form neutrons under extreme pressure. A typical neutron star is only about 20 kilometers in diameter, but can contain more mass than our Sun. Interestingly, some neutron stars can spin rapidly and emit beams of radiation, leading to their classification as pulsars. These fascinating objects can last for millions, even billions of years after the supernova, essentially surviving the explosive event. Black holes, on the other hand, represent a different but equally intriguing outcome. When the core collapses to the point where gravity is so intense that not even light can escape, a black hole forms. While the star, as we perceive it, no longer exists, the black hole represents a remnant that continues to exert its gravitational influence on the surrounding space. Its intriguing nature keeps scientists engaged in studying how such entities interact with their environments, including interactions with companion stars or accreting material from nearby cosmic structures. Thus, while the original star does not survive the supernova in its prior state, remnants like neutron stars and black holes embody the next phase of stellar evolution that continues to influence the cosmos long after the tremendous explosion. These fascinating remnants contribute to the ongoing story of stellar life and death, emphasizing the complexity of the universe. Brown dwarfs occupy a unique position in the spectrum of celestial objects, falling between the largest planets and the smallest stars. Often described as failed stars, these intriguing entities form from the same processes as stars, beginning as clouds of gas and dust collapsing under their own gravity. However, they do not gather enough mass to initiate sustained hydrogen fusion at their cores, which is necessary for true stellar classification. Instead, their mass typically falls between about 13 and 80 times that of Jupiter, marking them too large to be classed as planets, but not quite massive enough to be considered full-fledged stars. Detecting brown dwarfs proves challenging primarily due to their inherent characteristics. They do emit some heat generated during their formation, but this thermal radiation is often faint and diminishes over time as they cool. Unlike stars that shine brightly through nuclear fusion, brown dwarfs have lower luminosity and may blend seamlessly into the background when observed with traditional telescopes. This dimness makes them less detectable compared to other celestial bodies and contributes to their elusive nature. Additionally, brown dwarfs tend to form in environments that complicate their identification. They are often found in star-forming regions where many other objects are present, creating a crowded backdrop that makes it hard to isolate and pinpoint individual brown dwarfs. Moreover, they can be quite distant from Earth, further diminishing the chances of detection with conventional optical telescopes. Astronomers have developed specialized techniques to identify these enigmatic objects, often leveraging infrared observations, since brown dwarfs emit most of their energy in the infrared spectrum rather than visible light. With advancements in technology and observational capabilities, our ability to detect and study brown dwarfs has improved, leading to a growing catalogue of these fascinating objects. They play a significant role in astrophysics, helping to refine our understanding of star formation processes and the diversity of objects in the universe. Massive stars are known for their powerful stellar winds, which are streams of charged particles that flow away from the star at incredible speeds. These winds result from the intense energy and pressure created in the outer layers of such stars. Unlike less massive stars, which generate winds through more subtle processes, the stellar winds from massive stars are driven by their extreme temperatures and luminosities. The primary mechanism behind the production of stellar winds in massive stars involves radiation pressure. In these stars, nuclear fusion occurs at an astonishing rate, generating immense amounts of energy that create significant outward pressure on the outer layers. The intense radiation produced generates high-energy photons, which can impart momentum to the particles in the star's atmosphere. This radiation pressure becomes strong enough to overcome the star's gravitational pull, allowing material to be ejected into space. As a result, the outer layers of the star expand, losing mass to the surrounding environment. In addition to radiation pressure, the stellar winds from massive stars are influenced by their internal structure and the role played by magnetic fields. The convective motions within these stars can create turbulence, which helps in driving material outward. Furthermore, if a massive star possesses a strong magnetic field, it can interact with the stellar wind, influencing its direction and velocity. This interaction may lead to the formation of shocks and other complex phenomena within the stellar wind. The consequences of stellar winds from massive stars are substantial. Not only do these winds contribute to the chemical enrichment of the interstellar medium by dispersing elements formed within the star, but they also play a crucial role in the dynamics of galaxy formation and evolution. As massive stars eventually reach the end of their life cycles and explode as supernovae, the material they have expelled contributes significantly to the cosmic ecosystem, paving the way for new star and planet formation. The study of stellar winds provides essential insights into the life cycle of massive stars and their impact on the universe. Dark energy is an enigmatic force that constitutes about 70% of the total energy density of the universe, yet remains one of the most profound mysteries in cosmology. Discovered through observations of distant supernovae and the cosmic microwave background radiation, dark energy is thought to be responsible for the accelerated expansion of the universe, a phenomenon revealed by the work of astronomers in the late 20th century. When we observe distant galaxies, we see that they are moving away from us, and the farther they are, the faster they seem to be receding. This observation leads to the conclusion that the universe is expanding. Initially, it was believed that this expansion was slowing down due to the gravitational attraction of all matter present in the universe. However, studies indicated that not only is the universe expanding, but the rate of this expansion is actually increasing over time. Dark energy provides the explanation for this acceleration, acting as a sort of anti-gravitational force that pushes galaxies apart. The nature of dark energy is still not fully understood, prompting a range of theories among scientists. Some propose that it could be a constant energy density filling space uniformly, often associated with the cosmological constant, a concept introduced by Albert Einstein during his work on general relativity. Other theories suggest that dark energy could be dynamic, changing over time and influencing the expansion in different ways. Regardless of its specific nature, the existence of dark energy has transformed our understanding of the universe, indicating that a significant portion of the cosmos behaves in ways that challenge our conventional notions of gravity and matter. The implications of dark energy extend beyond just cosmic expansion. They influence the ultimate fate of the universe itself. If dark energy continues to dominate, the universe may keep expanding indefinitely, leading to scenarios like the Big Freeze, where galaxies drift further apart and stars eventually burn out. The search for a deeper understanding of dark energy highlights the ongoing quest in cosmology to unravel the complex and often surprising nature of the universe we inhabit. The formation of the first stars, often referred to as population 3 stars, marks a pivotal moment in the history of the universe. This event occurred roughly 500 million to 1 billion years after the Big Bang, during a period known as the Cosmic Dawn. At this time, the universe was composed mainly of hydrogen, helium, and trace amounts of lithium, with little to no heavy elements, which are formed later in stellar evolution. Understanding how these primordial stars came to be involves exploring the conditions of the early universe. Initially, small density fluctuations in the nearly uniform distribution of gas following the Big Bang began to collapse under their own gravity. The process started in regions where dark matter had formed clumps, creating gravitational wells that attracted the surrounding gas. As gas fell into these wells, it grew denser and hotter. Eventually, when temperatures in the core reached critical levels, hydrogen atoms began to fuse into helium, marking the birth of the first stars. This fusion caused these stars to be extremely massive and luminous, leading to unique evolutionary paths. The first stars were likely very different from those we see today. They were not only massive but also burned out quickly, leading to rapid life cycles. These stars produced and released vast amounts of energy and heavy elements into the surrounding interstellar medium when they exploded as supernovae at the end of their brief lives. This process enriched the cosmos with heavier elements, paving the way for the formation of subsequent generations of stars and ultimately galaxies, planets, and life as we know it. The search for evidence of these first stars is ongoing, with astronomers utilizing powerful telescopes to look back in time and observe distant galaxies. The study of these early stars offers valuable insights into the processes of star formation, galaxy evolution, and the chemical evolution of the universe itself, illustrating the intricate connections that led to the rich, diverse cosmos we see today. The first second after the Big Bang was an extraordinary moment in the history of the universe, characterized by rapid and profound changes. This period, often referred to as the Planck epoch, extends from the very moment of the universe's inception through to the end of the first second, encompassing a series of pivotal transformations. During this time, the universe began as an infinitely hot and dense point, filled with a high-energy state of matter and radiation. In the first fractions of a second, known as the quantum era, fundamental forces began to emerge. The four known fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, gradually separated from a unified state. At extremely high temperatures, reaching upwards of 1 trillion degrees Celsius, particles such as quarks and gluons formed and existed in a soup-like state. This chaotic environment made it impossible for matter as we know it to exist, as particles would continuously annihilate with their antiparticles, creating a constant cycle of energy and matter. As the universe expanded, it began to cool rapidly. Approximately 1 microsecond after the Big Bang, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. Within the first few minutes, during what is known as Big Bang nucleosynthesis, these protons and neutrons fused together to create the universe's first light elements, predominantly hydrogen, helium, and trace amounts of lithium. By the end of the first second, the universe was no longer a hot, dense plasma. It had expanded and cooled enough for electrons to combine with protons, forming neutral hydrogen atoms in a process called recombination. The universe had transitioned to a state where matter could begin to coalesce into the first atoms, setting the stage for the formation of stars and galaxies in the future. This critical early period laid the foundation for the complex and vast cosmos we witness today, illustrating the remarkable journey from a singular event to a diverse universe filled with matter and structure. The apparent imbalance between matter and antimatter in the universe remains one of the most profound and intriguing questions in modern cosmology and particle physics. According to current theories, the universe should have produced equal amounts of matter and antimatter during the Big Bang. Matter consists of particles such as protons and electrons, while antimatter consists of their counterparts, antiprotons and positrons. If they were created equally, they would annihilate each other upon contact, leaving behind radiation, thus resulting in a universe devoid of matter. However, we observe an abundance of matter, leading to the mystery of why there is more matter than antimatter. This discrepancy is often linked to a phenomenon known as baryogenesis, which refers to the processes that generated matter. To account for the excess of matter, scientists propose that certain conditions favored the production of baryons, which are particles that include protons and neutrons, over antibaryons. These conditions must have occurred during the early universe, specifically in the first few seconds after the Big Bang. Experimental observations suggest that some physical processes may exhibit a systematic preference for matter-producing interactions. One example of this is called CP violation, where the laws of physics treat matter and antimatter differently under certain conditions. This violation means that certain reactions involving particles do not mirror their counterparts involving antiparticles, contributing to the imbalance. While CP violation has been observed in specific particle decays, it appears insufficient to account for the observed degree of matter dominance, indicating that additional factors or unknown physics may be involved. Furthermore, theories involving inflation, a rapid expansion of the universe in its earliest moments, may also play a role in the matter-antimatter asymmetry. However, the mechanisms responsible for creating such a predominance of matter over antimatter remain an active area of research. Understanding why our universe is predominantly composed of matter could lead us to new insights into the fundamental nature of reality, revealing potentially undiscovered particles or interactions that govern these intriguing dynamics. The quest to answer this question underscores the complexity of the universe and our ongoing attempts to understand its origins. Dark matter remains one of the most elusive and enigmatic components of the universe, constituting about 25% of its total mass energy content. While it cannot be observed directly through electromagnetic radiation, such as light, its existence is inferred from gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Galaxies rotate at such speeds that, without additional unseen mass, they would tear themselves apart. This discrepancy leads scientists to theorize the presence of dark matter, which exerts gravitational influence without emitting light or interacting with other matter in ways detectable by conventional means. The true nature of dark matter is still an open question in astrophysics. Numerous candidates have been proposed to explain its existence. One leading hypothesis suggests that dark matter is composed of WIMPs, or weakly interacting massive particles. These hypothetical particles are predicted to have mass and interact via the weak nuclear force and gravity, making them incredibly difficult to detect. Numerous experiments are ongoing, attempting to directly observe WIMPs or their byproducts, though none have yet been conclusively identified. Another possibility involves lighter particles known as axions, which are theorized to arise from quantum chromodynamics, the theory that describes strong interactions in particle physics. If axions exist, they could provide a mechanism for dark matter while also explaining some theoretical puzzles in physics. On the larger scale, the existence of dark matter has significant implications for the evolution of the universe. It acts as a framework around which visible matter clusters, influencing the formation of galaxies and cosmic structures. Without dark matter, the universe's arrangement would differ dramatically, with galaxies not forming as they currently do. While advanced telescopes and experiments aim to shed light on the mysterious nature of dark matter, its true composition remains unresolved. The study of dark matter not only challenges our understanding of gravity and fundamental physics, but also pushes the boundaries of our knowledge about the universe, encouraging scientists to explore uncharted territories in cosmic inquiry. Each discovery related to dark matter enhances our understanding of the universe and offers clues that may one day lead to its identification. The concept of shadow galaxies, or galaxies composed entirely of dark matter, presents a fascinating idea in astrophysics, delving into the mysterious nature of dark matter and its role in the universe. While traditional galaxies are composed of stars, gas, dust, and dark matter, the proposition of shadow galaxies suggests a form of structure that exists solely within the dark matter domain, devoid of any visible matter as we understand it. Theoretically, these shadow galaxies could form in regions of space where dark matter is prevalent. Dark matter interacts primarily through gravity and does not emit or absorb light, making it invisible to standard astronomical observations. If a sufficient concentration of dark matter were to collapse under its own gravity, it could create a structure similar to a galaxy. However, unlike conventional galaxies that host stars and other visible components, a shadow galaxy would consist entirely of dark matter. The existence of such structures aligns with some cosmological simulations that incorporate dark matter. These simulations suggest that dark matter halos can form and clump together to influence the distribution of visible matter. In the case of shadow galaxies, they could potentially evolve as isolated entities within the cosmic web, existing in regions where normal matter is sparse. Despite their intriguing nature, these galaxies would remain challenging to detect, as they would not produce light or radiate energy in any detectable form. As current observational techniques rely heavily on detecting electromagnetic radiation from stars and gas, the search for shadow galaxies hinges on indirect evidence. Researchers might identify areas with gravitational effects that suggest the presence of additional mass without observable matter. These gravitational influences could hint at shadow galaxies interacting with normal matter, providing clues to their existence. While no direct evidence of shadow galaxies has yet been found, the ongoing exploration of dark matter and its role in cosmic structure formation reshapes our understanding of the universe. The possibility of shadow galaxies emphasizes the complexity and diversity of cosmic entities yet to be discovered, highlighting the universe's mysteries and the profound questions that drive scientific inquiry. Fast radio bursts, or FRBs, are among the most intriguing phenomena in the cosmos, characterized by brief but extremely powerful bursts of radio waves that can last only a few milliseconds. Discovered in 2007, these bursts of energy come from distant galaxies, and their sudden appearance has sparked intense research efforts to determine their origins. The exact mechanisms behind FRBs remain a subject of ongoing investigation, but several potential explanations have emerged. One leading theory suggests that FRBs could be produced by magnetars, which are highly magnetized neutron stars. These neutron stars have incredibly strong magnetic fields and can experience violent outbursts or starquakes that release vast amounts of energy. The model posits that when a magnetar undergoes such an event, it generates a burst of radio waves detectable across vast intergalactic distances. Observations have corroborated this theory, especially with the discovery of a repeating FRB linked to a magnetar in our own galaxy. Other hypotheses propose that FRBs could arise from colliding neutron stars, which are often the remnants of supernovae. When two neutron stars spiral toward each other and ultimately collide, they can produce immense energy, leading to the emission of radio waves and other electromagnetic radiation. Such cataclysmic events may result in short-lived bursts that resemble the characteristics of FRBs. Additionally, some scientists have explored the idea that FRBs could be linked to exotic astrophysical processes, such as interactions involving black holes or even phenomena related to cosmic inflation. The diversity of potential sources reflects the complexity of the universe and challenges researchers to develop methods for detecting and studying these fast radio bursts in greater detail. The quest to understand FRBs not only sheds light on these enigmatic bursts, but also holds broader implications for our understanding of the universe. By examining their properties and distribution, astronomers can gain insights into the evolution of galaxies, the structure of the intergalactic medium, and the physics of extreme environments. As technology advances, the mystery of fast radio bursts will continue to unfold, revealing new layers of knowledge about the cosmos. The formation of supermassive black holes in the early universe presents a compelling area of research, particularly given their presence in the centers of most galaxies, including our Milky Way. Observations have revealed supermassive black holes with masses equivalent to millions or even billions of times that of our Sun, existing less than 1 billion years after the Big Bang. Understanding how these colossal entities could form so rapidly poses intriguing questions about the conditions present in the young universe. One prevailing theory suggests that supermassive black holes might have originated from the direct collapse of massive clouds of gas in the early universe. After the initial formation of stars and galaxies, dense regions of gas could collapse under their own gravity to form massive seeds that eventually grew into black holes. This process could occur efficiently in the high-density environments of the early cosmos, where gas was abundant and cooled rapidly, allowing for direct collapse without necessarily forming stars first. Alternatively, the formation of supermassive black holes could involve the merging of smaller black holes, or the rapid accretion of matter onto a seed black hole. In this scenario, smaller black holes, possibly formed from the remnants of the first generation of stars, often massive and short-lived, could collide and merge over time, leading to the growth of supermassive black holes. As these black holes accumulated mass from their surroundings, such as from nearby gas and dust or through mergers with other black holes, they could accelerate their growth significantly. The role of the early universe's environment is also significant. The rapid expansion and cooling conditions created in the wake of the Big Bang led to the formation of dense molecular clouds, which could facilitate the processes of black hole formation and growth. Additionally, intense star formation rates in the early universe, alongside active galactic nuclei, may allow for high accretion rates, further contributing to the rapid emergence of supermassive black holes. Research continues to unveil the conditions that facilitated the existence of these intriguing objects so early in cosmic history. Observations of distant quasars powered by supermassive black holes provide valuable data that challenges our models and theories about galaxy formation and evolution, ultimately enhancing our knowledge of the universe's formative epochs. The mystery surrounding their early formation reflects the overarching complexity and dynamism of cosmic evolution. The Great Oxidation Event, also known as the Great Oxygenation Event or GOE, represents a significant turning point in Earth's history, occurring around 2.4 billion years ago. This period marks the first time that free molecular oxygen began to accumulate in the Earth's atmosphere in significant quantities, largely due to the evolution of photosynthetic microorganisms, particularly cyanobacteria. These organisms harnessed sunlight to convert carbon dioxide and water into organic matter, releasing oxygen as a byproduct. Before the GOE, Earth's atmosphere contained very little free oxygen, which posed limitations on the types of life that could flourish. The rise of cyanobacteria initiated a fundamental change in this dynamic. As these microorganisms spread across the oceans, their photosynthetic activity gradually increased the levels of oxygen in the atmosphere. This process was not immediate. It took several 100 million years for oxygen levels to rise significantly. The consequences of the Great Oxidation Event were profound, leading to widespread environmental and biological changes. One of the most critical impacts was the shift in the chemical composition of the atmosphere and oceans. Increasing oxygen levels resulted in the oxidation of iron present in the oceans, which led to the formation of substantial iron oxide deposits known as banded iron formations. These deposits are still visible today in the geological record, serving as evidence of the transition in Earth's atmospheric conditions. Biologically, the accumulation of oxygen opened the door for more complex life forms. While the initial rise in oxygen levels was likely toxic to many anaerobic organisms that thrived in low oxygen conditions, this shift eventually paved the way for aerobic organisms to evolve. Aerobic respiration, which utilizes oxygen to produce energy more efficiently than anaerobic processes, enabled the diversification of life forms and increased metabolic complexity. This event laid the foundational groundwork for the eventual emergence of multicellular organisms and, ultimately, terrestrial life. The Great Oxidation Event marked a critical juncture in Earth's development. By transforming the planet's atmosphere and biosphere, it initiated a cascade of evolutionary changes that shaped the trajectory of life on Earth, enhancing our current understanding of the complex interplay between biological processes and environmental changes in the history of our planet. The missing baryon problem highlights a puzzling discrepancy in our understanding of the universe's matter. Baryons are particles such as protons and neutrons, the building blocks of atoms, and they make up most of the observed mass in the universe. According to current measurements, baryonic matter should account for nearly 1/6 of the total energy density of the universe. However, when scientists tally the visible baryonic matter observed in galaxies and other structures, they find that a significant portion appears to be unaccounted for, hence the term missing baryons. One possible explanation for this conundrum lies in the presence of baryonic matter in regions that are difficult to detect. For instance, a significant amount may reside in the hot, diffuse gas between galaxies, known as the intergalactic medium. This gas, though composed of baryons, is often too diffuse and too hot to emit light that can be easily observed. Advances in astronomical techniques, such as X-ray observations, have begun to uncover this hidden baryonic matter, suggesting that it may indeed account for some of the missing mass. Furthermore, the formation of large-scale structures in the universe likely played a role in distributing baryons in ways that are not immediately visible. During the evolution of the cosmos, these baryons could have been expelled from galaxies due to powerful winds driven by star formation and supernova explosions, scattering them into the vast emptiness of space. This process could lead to baryons being present in less detectable forms, rather than tightly bound within stars and galaxies. As cosmologists continue to study the universe, the missing baryon problem serves as a compelling reminder of the complexity and mystery that still exists within our cosmic landscape. Discovering the whereabouts of these elusive baryons not only refines our understanding of the universe's matter content, but also informs the broader quest of understanding cosmic evolution and formation. Gravity's ability to bend light is a fascinating consequence of Einstein's theory of general relativity. According to this theory, massive objects like galaxies or clusters of galaxies warp the fabric of space-time around them. When light from a distant source, such as a far-off star or galaxy, passes near a massive object, the curvature of space-time causes the light's path to bend. This phenomenon occurs because light follows the natural curves of space-time, and thus what appears as a straight line in a conventional sense is actually altered when influenced by gravitational fields. Gravitational lensing can be classified into three main types: strong, weak, and microlensing. Strong lensing occurs when the gravitational field is particularly intense, leading to dramatic effects like the formation of multiple images of a distant object, arcs, or complete rings known as Einstein rings. This happens when the light source, the lensing mass, and the observer are nearly perfectly aligned. Weak lensing, on the other hand, creates subtle distortions of background galaxies, allowing astronomers to map the distribution of dark matter in the universe. Microlensing involves the bending of light from a background star due to the gravitational field of an object in the foreground, such as a planet, allowing researchers to detect otherwise hidden bodies. The consequences of gravitational lensing reach far beyond simply observing visual distortions. It serves as a powerful tool for astronomers, enabling them to study the universe in more detail. By analyzing the lensing effects, scientists can measure the mass of galaxies and clusters, which is crucial for understanding the distribution of both visible and dark matter. The light bending can even aid in the detection of exoplanets, as they occasionally amplify the light from distant stars when they align just right. As we continue to study these lenses, it becomes clear that gravity does not merely anchor celestial objects, but also plays a vital role in shaping our understanding of the cosmos. Gravitational lensing opens windows to the past, allowing us to peer deeper into the universe than ever before while revealing the intricate interplay between light and gravity on a grand scale. Traveling at the speed of light is a concept that stretches the boundaries of our understanding of physics. According to Einstein's theory of relativity, nothing with mass can achieve this phenomenal speed. As an object accelerates towards the speed of light, its mass effectively increases, requiring ever more energy to continue accelerating. To reach the ultimate speed limit of the universe, infinite energy would be needed, making such a journey impossible for any object with mass. including humans. Even if we could hypothetically contemplate traveling at the speed of light, the experience would be beyond our comprehension. For massless particles like photons, which undoubtedly travel at this speed, time experienced ceases to flow. From the perspective of light, the journey from one point in space to another occurs instantaneously, obliterating the concept of time altogether. For the traveler, there would no longer be a past or future. Everything would exist as a single, timeless moment. Additionally, moving at such remarkable speeds would dramatically alter one's perception of space. According to the principles of relativity, as an object approaches light speed, distances in the direction of travel would contract. This phenomenon is known as length contraction, resulting in distances appearing shortened, effectively bringing destinations closer together in a way that defies ordinary experience. However, this contraction is accompanied by immense energy requirements and logistical challenges that are currently insurmountable. While traveling at light speed remains firmly within the realm of theoretical speculation, it serves as a gateway to understanding the laws of physics that govern our universe. This exploration raises thought-provoking questions about the nature of time, space, and reality itself, pushing us to contemplate our place in the cosmos. The boundaries of human experience may limit us, but our curiosity and quest for knowledge are boundless, driving us to explore the very fabric of the universe. Time dilation is one of the most intriguing consequences of Einstein's theory of relativity, and it has significant implications for space travel. As an object moves closer to the speed of light, time for that object slows down relative to an observer who remains stationary. This means that astronauts traveling at high speeds would experience time differently than people on Earth. For example, while a few years might pass for the travelers, decades could pass for those remaining at home. This phenomenon was graphically illustrated in the thought experiment known as the twin paradox. In this scenario, one twin embarks on a journey into space at a velocity approaching that of light while the other remains on Earth. Upon the traveling twins' return, they would find that they have aged much less than their earthbound sibling. This time discrepancy is a vivid demonstration of how traveling at significant fractions of the speed of light can lead to profoundly different experiences and timelines. In practical terms, time dilation poses challenges for long-term space missions. If humanity were to explore distant galaxies or embark on journeys through interstellar space, astronauts would need to contend with the effects of time dilation as they travel at high speeds. For any crewed spacecraft venturing into deep space, careful planning and understanding of relativistic effects would be essential to manage the psychological and social implications of extended time away from Earth. As we consider future aspirations for space travel, time dilation emphasizes the need for innovative propulsion systems capable of approaching relativistic speeds. It also inspires more profound questions about our cosmic horizon, the nature of time itself, and how humanity will adapt to conditions that challenge our conventional understanding of aging and temporal perception. The vastness of space and the complexities of time remind us that exploration of the universe fundamentally alters our relationship with the passage of time. Gravitational waves are ripples in the fabric of space-time caused by accelerating massive objects, such as colliding black holes or neutron stars. Predicted by Albert Einstein in his general theory of relativity, these waves travel at the speed of light, carrying information about their origins and the properties of the objects that created them. When two massive bodies orbit each other and merge, they create disturbances in space-time that propagate outward, much like ripples created when a stone is thrown into a pond. Detecting these minute ripples poses a formidable challenge due to their incredibly small effect on space-time. The changes in distance caused by a gravitational wave can be as tiny as a fraction of the diameter of a proton. To achieve this sensitivity, scientists use highly sophisticated instruments like interferometers. The most prominent example is the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO. LIGO consists of two large facilities in the United States, equipped with arms several kilometers long arranged in an L shape. LIGO employs lasers and mirrors to measure the interference pattern of light beams split at the L's corner and sent down each arm. When a gravitational wave passes through, it slightly stretches one arm while compressing the other. This alteration changes the distance the light travels, resulting in a detectable shift in the interference pattern. The data collected is then analyzed to determine the characteristics of the gravitational waves, such as their amplitude and frequency, which provide insights into the events that caused them. Since the first detection of gravitational waves in 2015, scientists have observed multiple events, allowing for unprecedented insights into the universe. This new astrophysical tool enhances our understanding of cosmic events and opens up a new era in astronomy, enabling researchers to study some of the most violent and energetic processes in the universe. Gravitational waves not only confirm aspects of general relativity, but also revolutionize our observation of the cosmos, providing a unique perspective on events that are otherwise invisible, such as black hole mergers and neutron star collisions. Wormholes are fascinating theoretical constructs in physics that arise from the equations of general relativity. Essentially, a wormhole is a hypothetical tunnel-like structure that connects two separate points in space-time. If such structures exist, they could provide shortcuts through the universe, potentially allowing for faster-than-light travel between distant regions. However, the very possibility of wormholes entails significant scientific challenges and a few daunting questions. The concept of a traversable wormhole suggests that one could enter the wormhole at one end and emerge from the other almost instantaneously. This tantalizing idea has captivated the imagination of scientists and science fiction enthusiasts alike. However, for a wormhole to remain stable and usable for such travel, theoretical models propose that it would require exotic matter with negative energy density. This kind of matter has not yet been discovered and remains purely speculative. Another major hurdle in the concept of wormholes is their stability. Many solutions that allow for the existence of wormholes seem to imply that they would quickly collapse, making them impractical for any kind of transportation. Even if a stable wormhole could exist, it raises paradoxical questions about causality, such as potential time travel implications that could lead to inconsistencies in history. Despite these challenges, the notion of wormholes prompts profound discussions about the nature of space, time, and universe travel. They encourage scientists to explore the boundaries of general relativity and quantum mechanics, while inspiring creative approaches to understanding the cosmos. While wormholes might be far from being proven scientifically, they serve as a catalyst for innovative ideas about the structure of our universe and how we might interact with it in the future. The possibility of wormholes and their potential for faster-than-light travel continues to be a captivating area of research and speculation in modern theoretical physics. The expansion of the universe fundamentally alters our understanding of space-time. Coined as the Big Bang, the universe started from an extremely hot and dense state and has been expanding ever since. This expansion is not just a movement of galaxies through space. Rather, it is space itself that is stretching. As a result, the relationship between distance and time becomes complex and dynamic, influencing the very fabric of space-time. As the universe expands, galaxies and cosmic structures are moving away from each other. This phenomenon is described by Hubble's law, which notes that the farther away a galaxy is, the faster it appears to be receding. This doesn't imply that the galaxies are moving through space, but rather that the space between them is increasing. Consequently, measuring distances in the universe becomes interwoven with the effects of this expansion, complicating our perception of time and space on cosmic scales. Moreover, the expansion of the universe leads to the concept known as cosmological redshift. As light travels through the expanding universe, its wavelength is stretched, moving it to longer, redder wavelengths. This redshift provides crucial information about the speed at which objects are receding and helps astronomers understand the rate of expansion over time. It serves as a tool to trace the history of the universe and offers insights into its age and the forces impacting its growth. Additionally, the interplay between expansion and the geometry of space-time influences the overall fate of the universe. The presence of dark energy, a mysterious force driving the acceleration of this expansion, affects how space-time evolves on the largest scales. The ongoing research into dark energy reveals not only the complexities of space-time, but also resonates with the deeper questions surrounding the ultimate fate of the cosmos. As our understanding of the universe's expansion deepens, it continually reshapes our conception of space and time, leading us to reconsider our place in the vast expanse of existence. Traveling faster than light poses profound implications for our understanding of physics and the nature of reality itself. According to Einstein's theory of relativity, as an object approaches the speed of light, its mass effectively increases. This accumulation of mass requires exponentially increasing amounts of energy, making it impossible for any object with mass to actually reach or exceed this speed. However, if we entertain a hypothetical scenario in which faster-than-light travel were possible, several fascinating consequences emerge. One of the most notable implications of faster-than-light travel is the potential for causality violations. This means that events could be observed out of the traditional sequence of cause and effect. For instance, a traveler moving faster than light could arrive at a destination before their departure, raising paradoxes such as the well-known grandfather paradox, where actions taken in the past could retroactively change or negate the present. Such paradoxes challenge our foundational understanding of time and can complicate the very fabric of reality. Another consideration involves the concept of tachyons, hypothetical particles theorized to travel faster than light. These particles would have an imaginary mass and could theoretically allow for instantaneous communication across vast distances. However, their existence remains purely speculative, as they have yet to be observed or detected in any experimental situation. The implications of tachyons also raise questions about how information could be transmitted at faster-than-light speeds without violating causality. Additionally, if it were possible to bypass the light-speed barrier, this might open up new ways of exploring the universe. Concepts such as warp drives or wormholes could theoretically permit connections between distant points in space-time. Nevertheless, these ideas remain speculative and face numerous scientific challenges that have yet to be resolved. Widespread faster-than-light travel would transform our concepts of exploration, communication, and our very understanding of the universe. While faster-than-light travel remains firmly in the realm of theoretical discussion, pondering its possibilities invites intrigue and inspires deeper investigations into the principles of space, time, and our place within the cosmos. The quest for knowledge continues to unravel layers of our understanding, compelling us to question the nature of reality and our relationship with the universe. Gravity exerts a profound influence on the passage of time, a phenomenon predicted by Einstein's theory of general relativity. According to this theory, time flows more slowly in stronger gravitational fields. This means that the closer you are to a massive object, such as a planet or a star, the slower time passes relative to someone who is farther away from that object. This effect is known as gravitational time dilation, and it reveals the intricate connection between gravity and the flow of time. For example, consider a clock situated at sea level on Earth and another clock placed at a high altitude, such as on a mountain. The clock at a lower elevation, experiencing stronger gravitational pull, will tick slightly slower than the clock at a higher elevation. This dilation, although incredibly small in everyday experiences, has been measured with precision using atomic clocks and has implications for technology, particularly in global positioning systems or GPS. In more extreme situations, such as near a black hole, the effects of gravitational time dilation become even more pronounced. As objects approach the event horizon of a black hole, time for them slows dramatically compared to observers far from the gravitational influence of the black hole. This creates a fascinating scenario where time can be stretched to extreme limits, illustrating how gravity can warp the very fabric of space-time. These concepts challenge our intuitive understanding of time as a constant linear progression. Instead, they show how time is affected by the presence of mass and the structure of space around it. As our exploration of the cosmos continues, the understanding of how gravity shapes the passage of time deepens, revealing a dynamic interplay between dimensions that profoundly influences both the universe and our experience within it. The connection between mass, energy, and the curvature of space-time is a central tenet of Einstein's general theory of relativity. In simple terms, mass and energy can be thought of as sources of gravitational influence, causing the fabric of space-time to curve around them. This curvature dictates how objects move through space and experience time. According to the famous equation formulated by Einstein, energy and mass are equivalent, summarized by the realization that energy can be converted into mass and vice versa. This relationship is embodied in the equation that has become emblematic of modern physics, showing that a small amount of mass can be converted into a vast amount of energy. This equivalence means that not just massive objects, but also concentrated forms of energy, such as radiation, contribute to the curvature of space-time. As mass and energy create this curvature, they influence the motion of other objects nearby. For instance, planets follow curved paths around stars, which are products of the curved space-time created by the star's mass. In a way, we can think of gravity not as a force in the traditional sense, but as an effect of this curved space-time guiding the movement of objects. This framework helps explain phenomena such as orbits, gravitational lensing, and even the bending of light around massive objects. Moreover, the energy of a system can also influence space-time, as seen in cosmological scenarios where the energy density of the universe, including dark energy, drives its expansion. The effects of this expansion further illustrate the complex relationship between mass, energy, and the overall structure of space-time. As the universe evolves, the interplay between these elements informs not only the behavior of celestial bodies, but also shapes our broader understanding of the cosmos and the hidden dynamics at work in the universe. This deep connection remains foundational to the study of physics and our quest to comprehend the nature of reality. Black holes are some of the most fascinating and extreme objects in the universe, and they significantly distort space-time due to their immense gravitational pull. Formed from the remnants of massive stars that have undergone gravitational collapse, black holes possess an incredibly dense core, resulting in a gravitational field so strong that nothing, not even light, can escape from them once it crosses the event horizon, the boundary surrounding the black hole. As a black hole exists in space, its massive gravitational field warps the fabric of space-time in its vicinity. This distortion means that the geometry of space is altered, causing paths of objects and light that pass close to the black hole to curve dramatically. The stronger the gravitational pull, the more pronounced this curvature becomes. Objects that venture too close to a black hole can experience extreme gravitational effects, leading to phenomena like tidal forces, which stretch and compress objects in what is often referred to as spaghettification. The impact of black holes on space-time is not limited to their immediate surroundings. Their presence can influence the motion of nearby stars, gas clouds, and other celestial bodies, altering their trajectories. For instance, stars in close orbits around a supermassive black hole at the center of a galaxy can exhibit vast orbital velocities, providing evidence for the existence of the black hole. Observing the effects of such gravitational influences allows astronomers to infer the presence and mass of black holes that might otherwise remain hidden. Additionally, the study of black holes aids in understanding broader concepts of general relativity, particularly when it comes to extreme conditions. The warping of space-time around these enigmatic objects challenges our comprehension of gravity, time, and the interactions between them. As researchers continue to probe the mysteries of black holes, they not only expand our knowledge of these cosmic giants, but also inspire new questions about the very nature of the universe's structure and the fundamental laws that govern it. In our solar system, several intriguing locations present possibilities for the existence of life, often because they contain the essential ingredients for life as we understand it: liquid water, chemical nutrients, or energy sources. One of the most promising candidates is Europa, one of Jupiter's moons. Beneath its thick ice crust lies a vast ocean of liquid water, potentially harboring conditions suitable for life. The interaction between the ocean and Europa's rocky mantle could create an environment rich in the chemical reactions necessary for life, making it a prime target for astrobiological exploration. Another fascinating location is Enceladus, a moon of Saturn. Like Europa, Enceladus is believed to possess a subsurface ocean beneath its icy shell. Evidence of this ocean came to light through the discovery of plumes of water vapor and organic compounds erupting from its surface, hinting at hydrothermal activity on the ocean floor. The combination of water, energy, and organic molecules creates an enticing scenario for the potential of extraterrestrial life, prompting missions such as the proposed Europa Clipper and the Dragonfly mission to Titan. Titan, Saturn's largest moon, also stands out as a potential cradle for life. It possesses lakes of liquid methane and ethane on its surface, along with a dense atmosphere rich in organic compounds. While the environment is significantly different from Earth, some scientists propose that life could arise in non-water solvents, presenting a unique opportunity to study alternative biochemistries. Mars remains a traditional focus in the search for extraterrestrial life as well. Past missions have discovered evidence of ancient riverbeds and minerals that suggest the presence of water was once abundant. Current explorations aim to uncover signs of microbial life, both past and potentially extant, in subsurface reservoirs or briny environments where liquid water may still exist. The ongoing study of Martian soil, atmosphere, and potential cryovolcanic activity keeps the quest for life alive on our planetary neighbor. Each of these locations embodies unique environments that challenge our preconceptions about life beyond Earth. As technology advances and missions are conducted, the search for life in these varied settings continues to inspire and engage our curiosity about the broader universe and the potential for life beyond our home planet. Searching for biosignatures on exoplanets involves identifying specific chemical indicators and conditions that suggest the presence of life. Biosignatures are often defined as substances or patterns that are produced by living organisms, and scientists employ several methods and technologies to detect these signatures from light years away. One of the primary techniques is spectroscopy, which analyzes the light spectrum of a planet's atmosphere. By observing how light from a star passes through a planet's atmosphere, scientists can detect specific absorption lines corresponding to various gases. When examining exoplanets, researchers look for gases like oxygen, methane, and carbon dioxide, particularly in specific combinations that are indicative of biological processes. For example, on Earth, oxygen and methane coexist in notable amounts due to biological activity. Oxygen is produced by photosynthesis, while methane is generated by microbial organisms. The simultaneous presence of these gases on an exoplanet could signify potential biological activity, as they would generally react with each other and would not exist together in significant quantities in the absence of a replenishing source such as life. Telescopes capable of observing exoplanets, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, are equipped to conduct these spectral analyses. They focus on transiting exoplanets, which pass in front of their host stars, allowing some of the starlight to filter through the planet's atmosphere. As the light refracts through the atmosphere, scientists capture spectroscopic data to identify possible biosignatures. Additionally, missions to study moons and planets in our solar system, such as Europa and Enceladus, offer insights into biosignatures. These missions can look for microbial life in subsurface oceans or evaluate the chemical environments that might sustain life, providing comparative examples that inform the search for biosignatures beyond our solar system. While the quest to find biosignatures on distant exoplanets presents numerous challenges, Ongoing advancements in technology and observational techniques continuously enhance our capability to probe these worlds. As we refine our search strategies, the potential discovery of biosignatures could profoundly reshape our understanding of life's existence in the universe and our place within it. Microbial life on other planets could take on a diverse range of forms, shaped by the unique environmental conditions of each celestial body. Given the vast variety of extreme environments present in the universe, extraterrestrial microbes might not resemble anything we typically associate with life on Earth. Instead, they could manifest in ways that are adapted to harsh conditions such as high radiation, extreme temperatures, or unique atmospheric compositions. For example, microbial life on a planet like Mars, where surface conditions are cold and dry, might appear as hardy extremophiles analogous to Earth's tardigrades or certain bacterial spores. These microbes could develop thick protective cell walls or biofilms to conserve moisture and shield themselves from radiation. They might exist in subsurface aquifers where liquid water is present, entering a dormant state during harsh surface conditions and reviving when favorable conditions return. On moons such as Europa or Enceladus, where subsurface oceans exist beneath ice layers, microbial life could resemble organisms found in Earth's deep-sea hydrothermal vents. Extremophiles that thrive in these environments utilize chemosynthesis to convert chemical energy from mineral-rich waters rather than relying solely on sunlight. Such life forms may have unique adaptations, such as specialized enzyme systems to tolerate high pressures and cold temperatures. In contrast to Earth, where oxygen is a dominant gas due to photosynthetic organisms, microbial life on planets with different atmospheres could employ alternative metabolic processes. For instance, on a planet with high levels of methane, life forms could evolve to use methane as their primary energy source, resulting in biochemistry distinct from that on Earth. The physical appearance of such microbes could vary widely, depending on their metabolic pathways and how they interact with their environment, potentially taking on unique shapes, colors, or structures. Moreover, the search for microbial life involves considering the possibility of silicon-based organisms instead of carbon-based life forms, as silicon has some chemical similarities to carbon. This entirely different biochemical foundation could lead to life forms with unfamiliar characteristics. The diversity of planetary environments suggests that if microbial life exists elsewhere in the universe, it may present features and forms that challenge our understanding of what constitutes life. As we continue to explore other planets and moons, our pursuit of understanding microbial life encourages a broader perspective of biological possibilities. This exploration not only invites us to imagine what life could look like beyond Earth, but also deepens our appreciation for the resilience and adaptability of living organisms in varied environments. Distinguishing between biological and geological signatures from a distance is a significant challenge in astrobiology and planetary science. Scientists employ various methods and analytical techniques to analyze the chemical compositions and spectral signatures of celestial bodies, aiming to determine whether observed features are indicative of biological activity or purely geological processes. One of the primary tools used in this differentiation is spectroscopy. By analyzing the spectrum of light reflected or absorbed by a planet's atmosphere or surface, researchers can identify specific absorption lines associated with various chemical compounds. For example, gases such as oxygen, methane, and ozone can imply biological processes, as these are typically linked to the metabolic activities of living organisms. The simultaneous detection of both methane and oxygen is particularly compelling, as these gases tend to react chemically and are unlikely to coexist in stable amounts without a replenishing biological source. In contrast, geological processes can also produce certain gases and mineral signatures. For instance, volcanic activity can release gases like carbon dioxide and sulfur dioxide. In such cases, understanding the context of these emissions is crucial. Researchers analyze the surrounding geological features, composition, and the context of the detected signatures, seeking patterns or concentrations of signatures that are less likely to occur together geologically compared to biologically. Another approach involves examining the spatial distribution of materials. Biological signatures can often be localized or clustered in ways that differ from geological formations. For example, microbial mats on Earth exhibit specific patterns related to biological activity, whereas geological features would have a more consistent distribution. Furthermore, isotopic ratios can provide insights, as life processes tend to favor certain isotopes over others, which can be measured in atmospheric gases or surface materials. Continued advancements in space exploration technology enhance our ability to detect and analyze these signatures from afar. Spacecraft equipped with sophisticated spectrometers and imaging technologies will enable more detailed examinations of atmospheres, surfaces, and potential biosignatures on other planets and moons. Ultimately, the search relies on integrating multiple lines of evidence, combining atmospheric data, contextual geological information, and advanced analytical techniques to navigate the complex interplay between biological and geological signatures. As scientists deepen their understanding, the distinction between these two types of signatures becomes clearer, paving the way for future discoveries about life beyond Earth. Communicating with potential extraterrestrial intelligence poses a multitude of challenges, rooted in the vastness of space and the complexities of language and technology. The sheer distances involved can hinder any potential interaction. For example, our nearest stellar neighbor, Proxima Centauri, is more than 4 light-years away. This means that any signal sent from Earth takes over 4 years to reach that star, leading to lengthy delays in responses that could span decades or even centuries. Another significant challenge lies in the nature of communication itself. Life forms on other planets may have evolved entirely different ways of perceiving the universe. They might use forms of communication that are not vocal, such as light, sound in different frequencies, or even chemical signals. This raises the question of whether we would even recognize an extraterrestrial signal as communication in the first place, let alone understand its content. Furthermore, the concept of language may differ vastly between species, complicating our attempts to convey or interpret messages. If so, the technological aspect also plays a crucial role. Our current methods of sending signals, such as radio waves, may not be the right approach for all forms of intelligent life. Additionally, the possibility exists that extraterrestrial civilizations might have different technological advancements, rendering our signals indistinguishable from background noise to them. Without a common framework or understanding of technology, the potential for successful communication diminishes. Lastly, there are philosophical implications to consider. If an extraterrestrial civilization exists, will they even be interested in contacting us? Their motives, if they exist, may be completely alien to us. This leads to questions about the etiquette of communication and the possibility that an advanced civilization might choose not to disturb us by revealing their presence. All these aspects contribute to the intricate tapestry of challenges we face in the quest to establish contact with potential extraterrestrial intelligences. Preventing the contamination of other worlds with Earth life during space exploration is a critical aspect of planetary protection. This practice aims to preserve both extraterrestrial ecosystems and the integrity of scientific research. The fundamental approach begins before any mission is launched, involving rigorous planning and sterilization protocols for spacecraft and equipment. For instance, all tools, rovers, and landers must undergo cleaning procedures designed to eliminate microbes and organic materials that might hitch a ride to another planet or moon. The protocols are particularly stringent for missions targeting potentially habitable environments, such as Mars or the icy moons of Jupiter and Saturn. Each mission is classified according to its potential for contamination, which dictates the level of sterilization required. For example, missions that land on bodies believed to harbor life or where life could exist warrant the highest degree of protection. This means employing methods like dry heat sterilization, chemical cleaning agents, and rigorous microbiological testing to ensure that no Earth-originating life forms are present. Monitoring planetary environments is another essential component of avoiding contamination. If a spacecraft lands on a celestial body, scientists must be prepared to study it in a way that allows us to distinguish between Earth-based organisms and any native life forms. This consideration extends to our returning samples as well. Samples brought back to Earth from other worlds must be handled within specially designed containment facilities to prevent any potential biological contamination from escaping and affecting Earth's biosphere. Finally, the international nature of space exploration plays an important role in ensuring that planetary protection measures are upheld. Treaties such as the Outer Space Treaty emphasize that countries must avoid harmful contamination of space and celestial bodies. By fostering collaboration among nations and adhering to established protocols, the global community can work to protect both our own planet and the alien environments we seek to explore. The discovery of extraterrestrial life would profoundly reshape our understanding of biology and the principles governing life as we know it. Firstly, if we encounter life forms that have evolved independently of Earth, it would provide invaluable insights into the diversity of biological processes. This discovery could reveal entirely new biochemical pathways, alternative genetic structures, and different mechanisms of metabolism, challenging our current models of life that are primarily based on carbon and water. Moreover, the implications of finding life in extreme environments on other planets could expand our knowledge of the adaptability of life. For example, organisms thriving in harsh conditions, such as extreme temperatures, pressures, or radiation, might help us reassess the limits of life on Earth. Understanding how these extraterrestrial organisms survive and thrive could lead us to new biotechnological applications and inspire innovative solutions to environmental challenges on our own planet. Another critical aspect involves the evolutionary implications of extraterrestrial life. If we find organisms that exhibit a different evolutionary trajectory from Earth life, it would prompt a re-examination of the processes that drive evolution universally. Factors such as environmental pressures, genetic mutations, and evolutionary convergence could take on new meanings in this broader context, forcing us to consider whether similar life forms could arise across the cosmos, or if life's trajectory is uniquely tied to specific planetary conditions. Additionally, discovering intelligent extraterrestrial life could have profound philosophical implications, impacting our notions of intelligence, consciousness, and our place in the universe. It raises questions about the nature of intelligence itself, whether it is a common outcome of biological evolution or a rare phenomenon, and challenges the anthropocentric view of life. Ultimately, the existence of extraterrestrial life could lead to a deeper understanding of the fundamental principles of biology, enriching the tapestry of life and opening up possibilities we have yet to imagine. The definition of the habitable zone has undergone significant refinement since the concept was first introduced, evolving in tandem with our understanding of planetary science and astrobiology. Initially, the habitable zone, often referred to as the Goldilocks zone, was thought to be a simple region around a star where conditions might be just right for liquid water to exist on the surface of a planet, neither too hot nor too cold. This basic premise placed great emphasis on the presence of water as the key criterion for habitability, aligning closely with the conditions observed on Earth. As research progressed, scientists began to recognize that the concept of a habitable zone is much more complex than merely the distance from a star. It became clear that various factors affect a planet's ability to retain liquid water. These factors include a planet's atmospheric composition, pressure, and temperature, as well as its gravitational influence and geological activity. This acknowledgement expanded the criteria for habitability beyond mere proximity to a star, incorporating planetary characteristics that could foster or hinder the presence of water and, by extension, life. The advancement of technology and the discovery of exoplanets have also played a crucial role in redefining the habitable zone. The detection of planets with atmospheres rich in greenhouse gases, for instance, revealed that some planets could reside outside the traditional habitable zone, yet still harbor conditions suitable for life. Scientists now consider a broader framework that includes alternate climates and diverse environments, such as those on the ice-covered moons of the outer solar system, where subsurface oceans may exist beneath layers of ice. Furthermore, the definition has continued to evolve as discussions about life's potential forms expand. Astrobiologists are exploring the idea that life could exist in conditions previously dismissed as inhospitable. Consequently, the habitable zone is no longer a fixed boundary, but rather a spectrum that considers various environmental factors and potential biological adaptations. This dynamic understanding reflects our growing recognition of how diverse and adaptable life may be in the universe, highlighting that the search for extraterrestrial life must consider a wide range of possibilities beyond traditional definitions. Extremophiles play a transformative role in our search for extraterrestrial life by expanding the boundaries of what we consider habitable environments. These remarkable organisms thrive in conditions once thought to be inhospitable, such as extreme temperatures, pressures, acidity, salinity, and radiation. By studying extremophiles on Earth, scientists gain critical insights into the potential for life to exist in similar extreme environments elsewhere in the universe, such as the icy moons of Jupiter and Saturn or the surface of Mars. One significant contribution of extremophiles is their ability to survive conditions that challenge our traditional understanding of biology. For example, thermophiles thrive in hot springs and hydrothermal vents, while acidophiles flourish in highly acidic environments. Learning how these organisms adapt, metabolize, and reproduce sheds light on the mechanisms that allow life to persist in such harsh circumstances. This knowledge fuels theories about where life might exist beyond Earth, guiding missions to locations that may have once been overlooked due to their extreme conditions. Additionally, extremophiles serve as biological models in the search for life's potential signatures in extraterrestrial environments. Understanding the specific biochemical processes of extremophiles can help scientists identify potential biosignatures, indicators of past or present life, on other planets. For instance, the metabolic byproducts of extremophiles could inform the search for gases or organic compounds in the atmospheres of exoplanets, marking the presence of biological activity. This expands the criteria for detecting life, encouraging a broader search that considers life forms that may not resemble those on Earth. Lastly, extremophiles drive innovation in astrobiology and technology. Studying these organisms informs the development of biosensors and life detection instruments capable of identifying life in extreme conditions. Moreover, recent research into extremophiles has led to advances in fields such as biotechnology, where their unique properties can be harnessed for applications ranging from bioremediation to pharmaceuticals. As our understanding of extremophiles continues to grow, they remain essential allies in the pursuit of understanding life's adaptability and resilience throughout the cosmos. Preparing for the possibility of discovering extraterrestrial life involves a multifaceted approach that encompasses scientific, ethical, and societal considerations. One of the primary avenues of preparation comes from enhancing our scientific tools and methodologies for exploring the cosmos. This includes developing advanced telescopes, spacecraft, and instruments capable of detecting biosignatures, organic molecules or gases that may indicate biological activity. Initiatives like the James Webb Space Telescope and missions aimed at Mars and the icy moons of Jupiter and Saturn are crucial in this regard, allowing us to gather data that may lead to significant discoveries. Education and interdisciplinary collaboration are also key components in our preparation efforts. By fostering dialogue among fields such as astrobiology, planetary science, sociology, and ethics, scientists can better understand the implications surrounding the discovery of extraterrestrial life. This collaboration encourages the sharing of knowledge and ideas, leading to innovative approaches that tackle the complexities of such a discovery. Workshops, conferences, and outreach programs help prepare both the scientific community and the public for the possibilities that lie ahead. Ethics plays a critical role in preparing for contact with extraterrestrial life. Establishing ethical guidelines for the exploration and study of potential alien beings is essential, particularly in considering how to treat any discovered life forms. Discussions about planetary protection protocols, particularly concerning contamination of both Earth and extraterrestrial environments, ensure that we proceed responsibly in our search. The international scientific community is urged to engage with policymakers to develop frameworks that promote ethical conduct in the event of a discovery. Finally, public engagement and communication strategies are important as we prepare for the possibility of discovering extraterrestrial life. Transparency in sharing findings and developments helps manage public expectations and addresses concerns that may arise. Furthermore, educational initiatives aimed at informing the public about astrobiology and the implications of discovering life beyond Earth can foster a greater appreciation for the universe's complexity. Through these combined efforts, scientific, interdisciplinary, ethical, and communicative, we can approach the profound possibility of finding extraterrestrial life with readiness, curiosity, and responsibility. If a giant solar flare were to hit Earth, the impact could be both immediate and far-reaching, disrupting technology and infrastructure that modern society relies upon. Solar flares are massive bursts of energy from the sun that release radiation across the electromagnetic spectrum, including electromagnetic waves, X-rays, and gamma rays. When a particularly large solar flare occurs, it can produce a coronal mass ejection, where a significant amount of solar plasma is expelled into space. If directed towards Earth, this material can collide with our planet's magnetic field, leading to intense geomagnetic storms. One of the most noticeable effects of a solar flare hitting Earth would be the disruption of satellite systems. Satellites are crucial for communication, navigation, and weather observation, and a powerful solar flare could impair their functionality. Radio communications might be interrupted, and global positioning system accuracy could decline, leading to potential chaos in navigation and transportation systems. Moreover, astronauts on the International Space Station or other missions beyond Earth's atmosphere would be at an increased risk due to enhanced radiation exposure, necessitating safety protocols. On a larger scale, geomagnetic storms driven by a solar flare can also impact electrical grids on Earth. The induced magnetism can cause fluctuations in electrical currents, potentially damaging transformers and leading to widespread power outages. Past solar storms have demonstrated this reality. For instance, a severe event in 1989 caused a blackout across Quebec, affecting millions of people. Utilities must prepare for these scenarios by implementing preventive measures, such as protective circuitry and operational protocols during solar events. In addition to technological disruptions, solar flares can also create stunning visual phenomena, such as intensified auroras near the polar regions. While these light displays are among the more benign effects of solar activity, the broader implications highlight the reliance of contemporary society on technology that is vulnerable to cosmic phenomena. As our understanding of solar flares and their impacts grows, so does the importance of monitoring solar activity and developing strategies to mitigate the risk of future disruptions. Potentially hazardous asteroids pass near Earth more frequently than one might expect, although the vast majority pose little to no threat to our planet. NASA defines a potentially hazardous asteroid as any near-Earth object that comes within approximately 4,800,000 kilometers of Earth's orbit and measures at least 150 meters in diameter. This definition helps scientists identify objects that could cause significant damage if they were to collide with Earth. On average, astronomers detect a few dozen potentially hazardous asteroids each year. As observation technology improves, these numbers continue to rise. Currently, there are thousands of known near-Earth objects, with several hundred classified as potentially hazardous. Most of these asteroids follow stable orbits that keep them far from Earth. However, Gravitational interactions with other celestial bodies can alter their paths, making ongoing monitoring crucial. The frequency with which these objects approach varies. Some may make close passes every few years, while others could take centuries to orbit back to a position near Earth. The distances of their approaches can range from a few thousand kilometers to millions, and while many are monitored closely, it's essential to remain vigilant. The potential for larger asteroids to cause catastrophic impacts, albeit rare, necessitates a dedicated effort to track these objects and assess any potential risks they may pose. To ensure safety and preparedness, space agencies around the world have developed robust observation programs aimed at detecting and tracking near-Earth objects. Programs such as NASA's Near-Earth Object Observations aim to identify, characterize, and catalog these asteroids, ensuring that as many as possible are known well in advance. This ongoing surveillance not only helps in assessing risks, but also allows scientists to plan potential deflection strategies should a dangerous asteroid be identified in the future. A nearby gamma-ray burst could have catastrophic effects on Earth, depending on the proximity and intensity of the event. Gamma-ray bursts are among the most energetic events in the universe, resulting from the collapse of massive stars or the merger of neutron stars. When these explosive phenomena occur, they release a concentrated beam of gamma radiation that can travel across vast cosmic distances. If such a burst were to be directed toward Earth and occurred within a distance of just a few thousand light-years, the consequences could be dire. One of the primary effects of a nearby gamma-ray burst would be the ionization of our atmosphere. The intense radiation might strip away significant amounts of the ozone layer, which serves as a protective barrier against harmful ultraviolet radiation from the sun. A diminished ozone layer could lead to increased UV exposure, resulting in higher rates of skin cancer and other UV-related health issues for living organisms. Additionally, the environment would suffer as plant life becomes threatened, disrupting ecosystems and altering the balance of life on Earth. The radiation produced by a gamma-ray burst could also have direct impacts on biological systems. Humans and other life forms are highly sensitive to radiation, and a sudden surge could disturb cellular processes. Even if life were to survive, the pronounced ecological effects could lead to a mass extinction event, similar to those in Earth's history caused by significant environmental changes. Moreover, the electromagnetic pulse produced by the burst could induce electrical disruptions on Earth. This effect might lead to widespread failures in power grids and satellite communications, destabilizing technology and infrastructure essential for modern society. The consequences would not only have immediate impacts on daily life, but would also hinder recovery efforts and exacerbate the ongoing challenges of living in a post-burst environment. Overall, while gamma-ray bursts are rare and often occur far from Earth, their potential effects underscore the vulnerability of our planet to cosmic events. Continued research into these phenomena enhances our understanding and helps to prepare for the unexpected challenges posed by the universe. A rogue planet, which is a planet that does not orbit a star and instead drifts through interstellar space, could indeed enter our solar system, although such an event would be incredibly rare. If a rogue planet were to venture into our solar system, the consequences would depend on its size, trajectory, and speed, as well as the gravitational influences of the other planets. As a rogue planet approached, its gravitational pull could potentially disrupt the orbits of nearby celestial bodies. Depending on its size, the rogue planet could interact significantly with the orbits of the outer planets, possibly altering them and leading to chaotic gravitational interactions. This could result in destabilized orbits of nearby objects, including comets and asteroids, which might be flung into the inner solar system or thrown out into interstellar space. Such changes could lead to an increased risk of collisions between these bodies and Earth. If the rogue planet were to get close enough, it may also have dramatic effects on the Oort cloud, a distant region of icy bodies that surrounds our solar system. The gravitational influence of the rogue planet could disturb this cloud, sending a barrage of comets toward the inner solar system. These comets could pose a significant threat to Earth, leading to potential impact events that could endanger life. On a more fantastical note, if the rogue planet entered our solar system at a high velocity, it might not remain for long. It could pass through and then exit the solar system, leaving little lasting impact beyond some transient gravitational effects. However, if it were to enter on a collision course with a planet like Jupiter or even Earth, the outcomes could be more catastrophic, depending on the scale of the interaction. Regardless, while the idea of a rogue planet wandering into our solar system is intriguing, the likelihood of such an event significantly affecting Earth or our planetary neighborhood remains extremely low. Ongoing observations and research into celestial dynamics help to ensure that we understand these cosmic phenomena and their potential implications. Cosmic radiation presents significant long-term health risks to space travelers, primarily due to the exposure to high-energy particles originating from outside Earth's atmosphere. Unlike the relatively controlled environment provided by Earth's magnetic field and atmosphere, astronauts in space are subjected to continuous exposure to cosmic radiation, particularly on missions beyond low Earth orbit, such as trips to the Moon or Mars. The two primary types of cosmic radiation are galactic cosmic rays and solar particle events, both of which come with their own set of hazards. One of the most concerning long-term effects of cosmic radiation is an increased risk of cancer. The high-energy particles can damage DNA within cells, leading to mutations. Over time, this accumulation of damage can trigger the development of cancerous cells. Research indicates that the risk of developing cancer could rise significantly with prolonged exposure, particularly for missions that last for several months or years. This increased risk necessitates that mission planners develop strategies to minimize exposure, such as designing spacecraft with better radiation shielding or planning missions to occur during periods of lower solar activity. In addition to cancer, long-term exposure to cosmic radiation can lead to other health issues affecting the central nervous system and cognitive function. Some studies have indicated that cosmic radiation may impair brain function, potentially leading to issues such as memory loss or difficulties with spatial orientation. These effects can critically impact an astronaut's performance and decision-making abilities during missions, making it essential to conduct further research into mitigating these risks. Another significant concern is the impact of cosmic radiation on the cardiovascular system. Changes to the heart and blood vessels have been observed in animal studies exposed to cosmic radiation, suggesting that astronauts may be at an increased risk for cardiovascular diseases over time. This multifaceted risk profile highlights the necessity of ongoing research into protective measures for astronauts who will travel deep into space, ensuring the health and safety of future explorers as humanity ventures further into the cosmos. Such efforts will be critical for the long-term sustainability of human presence in space and the success of future long-duration missions. Supernovae have profound and far-reaching effects on their surrounding space environment, shaping the dynamics of galaxies and influencing the formation of new stars and planetary systems. When a massive star runs out of nuclear fuel, it undergoes a spectacular explosion known as a supernova, resulting in the expulsion of a tremendous amount of material and energy into the interstellar medium. This explosion releases shock waves that travel at incredibly high speeds, compressing nearby gas and dust and triggering the formation of new stars in regions previously devoid of significant activity. One of the immediate impacts of a supernova is the dispersal of heavy elements into space. During the stellar life cycle, massive stars synthesize elements such as carbon, oxygen, and iron through nuclear fusion. When a supernova occurs, these newly formed elements are released into the surrounding environment, enriching the interstellar medium with the building blocks necessary for forming planets and life as we know it. This cosmic recycling process is vital for the chemical evolution of galaxies, as it contributes to the diversity of elements available for subsequent generations of stars and planets. Additionally, the shock waves generated by the supernova can clear out regions of gas and dust, sweeping away materials that may inhibit star formation. As these shock waves expand, they create bubbles in the interstellar medium, leading to compressions that can ignite star formation in adjacent regions. This phenomenon often results in the creation of supernova remnants, which can become sites of new stellar nurseries, where hydrogen gas collapses under gravity to form new stars. Supernovae also play a critical role in regulating the structure of galaxies. The energy released can influence the dynamics of the interstellar medium, providing pressure that counteracts gravitational collapse in certain areas. This interaction helps maintain a balance within galaxies, impacting their morphology and evolution over billions of years. As a result, supernovae are not merely destructive events, but rather essential catalysts for the ongoing cycle of stellar birth, life, and death, contributing to the dynamic evolution of the universe. If two neutron stars were to collide near our solar system, the event would be a staggering display of cosmic violence, with consequences that could extend far beyond their immediate vicinity. Neutron stars are remnants of massive stars that have undergone supernova explosions, collapsing into incredibly dense objects primarily composed of neutrons. When two of these stars merge, they produce a burst of energy and gravitational waves that can be detected across vast distances in the universe. The most immediate effect of such a collision would be the release of a tremendous amount of gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. These waves travel at the speed of light and can distort space, potentially detectable by instruments like LIGO and Virgo, which monitor for such signals. A nearby neutron star merger would provide a unique opportunity for astronomers to observe and study these phenomena, furthering our understanding of fundamental physics. In addition to gravitational waves, the merger would also result in the release of a significant amount of gamma radiation and other electromagnetic waves. This burst of energy could create a gamma-ray burst, one of the most luminous explosions in the universe. If a gamma-ray burst were directed toward Earth, the intense radiation could have catastrophic effects on our atmosphere. This could lead to the depletion of the ozone layer, increasing harmful ultraviolet radiation reaching the surface, which could result in severe ecological consequences and pose significant health risks to living organisms. The merger of neutron stars also produces heavy elements through a process known as R-process nucleosynthesis. The aftermath of such a collision enriches the surrounding space with elements like gold, platinum, and uranium. If this event occurred close enough to our solar system, it would contribute to the cosmic abundance of these elements, potentially affecting the chemistry and formation of new stars and planetary systems in the region over time. While the likelihood of such a catastrophic event happening close to our solar system is extremely low, it serves as a reminder of the dynamic and often violent nature of the universe. The study of neutron star collisions offers valuable insights into stellar evolution, the behavior of matter under extreme conditions, and the processes that govern the creation of heavy elements. Coronal mass ejections, or CMEs, are significant bursts of solar wind and magnetic fields rising above the solar corona or being released into space. When these massive bursts occur, they can have profound effects on Earth and our technology. A CME typically consists of 1 billion tons of plasma and can travel at speeds of up to 3 million miles per hour, reaching Earth within 1 to 3 days after the event. When a CME interacts with Earth's magnetic field, it can trigger geomagnetic storms. These storms have the potential to disrupt satellite communications, GPS signals, and even power grids. Geomagnetic storms can induce electric currents in power lines, which may overload transformers and lead to widespread power outages, similar to the incident in 1989 when a CME caused a blackout in Quebec. As more of our critical infrastructures depend on technology reliant on electricity and satellite systems, the risks associated with CMEs have become a point of increasing concern for utility companies and governments. Additionally, CMEs pose risks to astronauts and space missions. The high-energy particles present in a CME can pose health hazards to astronauts working outside the protection of spacecraft, potentially leading to acute radiation sickness or increasing the risk of cancer from prolonged exposure. Space agencies closely monitor solar activity to give astronauts adequate warnings and ensure they can take necessary precautions, such as sheltering in safe zones within spacecraft during heightened solar activity. On a more positive note, CMEs can also enhance the beauty of our night skies. When the charged particles from a CME collide with Earth's atmosphere, they can create spectacular auroras near the polar regions. These natural light displays, known as the aurora borealis and aurora australis, occur when the particles excite gas molecules in the atmosphere, leading to colorful emissions of light. While CMEs present challenges to our technology, they also reveal the dynamic and intricate relationships between our planet and the Sun, highlighting the importance of continued monitoring of solar activity for predicting and mitigating potential impacts on Earth. A polar shift, often referred to as geomagnetic reversal, occurs when the Earth's magnetic north and south poles flip. This phenomenon has happened multiple times throughout Earth's history, with the last reversal occurring approximately 780,000 years ago. While such an event is a natural process, the potential consequences of a polar shift could be profound and multifaceted. One significant consequence could involve disruptions in the Earth's magnetic field, which acts as a protective shield against cosmic radiation and solar winds. A weakened magnetic field during a polar shift could expose the Earth to higher levels of solar and cosmic radiation. This increase in radiation has the potential to impact both biological systems and technology, possibly leading to higher rates of skin cancer and other health issues in humans and animals, as well as affecting satellite operations and aviation systems that rely on stable navigational data. Another potential impact of a polar shift is related to climatic changes. While the magnetic poles shifting does not directly affect the planet's axis or climate, the alteration in magnetic fields can influence atmospheric patterns over long timescales. Changes in the magnetic field could lead to alterations in jet streams and weather patterns, potentially resulting in more extreme weather events or shifts in climate zones. This might cause challenges for ecosystems and agriculture, as species would need to adapt to new environmental conditions. Additionally, societal infrastructure that relies on magnetic compass navigation or magnetism for functioning may be heavily affected. As the magnetic field fluctuates, navigational systems, including those used in aviation, maritime navigation, and even land-based travels, could experience inaccuracies. Depending on the timing and awareness of these changes, modifications to technology and navigational protocols might need to be implemented to maintain safe operations. While a polar shift is a natural and gradual process that typically unfolds over thousands of years, understanding its potential consequences can help societies prepare for the implications. Continued research into geomagnetic reversals allows scientists to better predict and understand the long-term impacts on the environment and technology, fostering resilience against possible disruptions that might arise during such an event. Tracking and predicting potentially dangerous space weather involves a combination of observational technologies, satellites, and data modeling. Space weather primarily pertains to phenomena such as solar flares, coronal mass ejections, and solar wind, all of which can impact Earth's magnetic field and atmosphere. The quest for reliable forecasts begins with monitoring solar activity using a network of ground-based observatories and space-based instruments. One of the key players in space weather monitoring is the National Oceanic and Atmospheric Administration's Space Weather Prediction Center, as well as NASA's Solar Dynamics Observatory and the European Space Agency's Solar and Heliospheric Observatory. These satellites provide real-time data about solar flares and other solar phenomena by capturing images in various wavelengths. This information helps scientists identify when the Sun is exhibiting heightened activity, allowing for early warnings about possible coronal mass ejections that could be directed toward Earth. Data from these observations are combined with advanced modeling techniques to forecast the potential effects of solar activity. Numerical models simulate how solar emissions travel through space and interact with the Earth's magnetic field. They utilize established scientific principles to predict the timing, intensity, and potential impact of space weather events. Furthermore, forecasters analyze historical data and trends to estimate the likelihood of certain space weather occurrences based on current solar conditions. To disseminate information about potential space weather hazards, various agencies issue alerts and advisories to industries and organizations that depend on technology vulnerable to space weather impacts. This includes the aviation sector, power grid operators, and satellite communications providers. By providing timely alerts, these agencies enable sectors to take protective measures, such as adjusting satellite orbits or temporarily shutting down sensitive systems during significant solar events. The ongoing advancements in observational technologies and data analysis continue to enhance our ability to predict space weather. As our understanding of the sun's behavior improves, the capacity to track and forecast potentially dangerous space weather becomes increasingly sophisticated, leading to enhanced preparedness and mitigation strategies for populations and industries reliant on technology. Terraforming Mars to make it habitable is a complex and ambitious endeavor that involves altering the planet's environment to create conditions suitable for human life. The primary goals include increasing surface temperatures, thickening the atmosphere, and introducing liquid water. Various strategies have been proposed to achieve these objectives, but each comes with its own set of challenges and ethical considerations. One promising approach to warming Mars involves greenhouse gas emissions. By releasing gases such as carbon dioxide, methane, and ammonia into the Martian atmosphere, we could enhance the greenhouse effect to raise surface temperatures. One option is to deposit large amounts of CO2 from polar ice caps, or utilize technologies to manufacture such gases. This could also involve redirecting asteroids rich in volatiles to collide with Mars, releasing their gases into the atmosphere. Over time, this process could thicken the atmosphere and raise temperatures enough to stabilize liquid water on the surface. Next, tackling Mars' thin atmosphere is crucial for creating a habitable environment. Currently, the Martian atmosphere is dominated by carbon dioxide and lacks sufficient pressure to support liquid water. To address this issue, scientists propose generating a thicker atmosphere by releasing gases that can trap heat, or by constructing large industrial facilities to produce and maintain the necessary atmospheric components. In addition, protecting the atmosphere from solar winds, which increasingly erode Martian gases due to its weak magnetic field, could be achieved through the installation of artificial magnetic fields or other stabilization technologies. Water is essential for any terraforming effort, and while Mars possesses polar ice caps, transporting water to other regions may be necessary for creating stable lakes or oceans. Terraforming strategies could include warming the ice caps to release water vapor or melting subsurface ice through geothermic activities. This liquid water could eventually support a biosphere, introducing microbial life forms that can enhance soil quality and prepare the environment for more complex life. While the idea of terraforming Mars captivates the imagination, it also raises ethical dilemmas. The prospect of altering another world for human habitation invites questions about our responsibility to any indigenous Martian life forms that might exist, as well as the long-term sustainability of such efforts. Engaging with these ethical considerations while pursuing scientific advancements is crucial for ensuring that any plans for terraforming are executed thoughtfully and responsibly. Ultimately, while the vision of a habitable Mars is exciting, it also involves a staggering array of challenges that require careful planning and international cooperation to realize. Establishing a permanent lunar base presents a range of significant challenges that encompass technological, logistical, and environmental factors. One of the most pressing concerns is the harsh lunar environment itself. The Moon experiences extreme temperatures, ranging from about -250 degrees Fahrenheit during the night to over 200 degrees Fahrenheit during the day. Such temperature fluctuations pose severe challenges for habitable structures and require advanced insulation and thermal management technologies to ensure the safety and comfort of astronauts over extended periods. Furthermore, the Moon has a very thin atmosphere, which means there is little protection from cosmic radiation and solar particles. This exposure poses serious health risks to astronauts living on the lunar surface. Effective shielding will be crucial, whether through designing habitats using lunar regolith, the Moon's natural soil, or deploying other protective materials. Developing technologies that can provide safe living conditions while maintaining a sustainable life support system is essential for long-term habitation. Logistical challenges are also significant when establishing a permanent base on the Moon. Transporting the necessary materials for construction, habitat modules, and supplies for life support systems involves substantial logistical planning and resources. Delivering equipment and personnel from Earth to the Moon regularly could be costly and complicated, necessitating efficient supply chains and reliable transportation methods. Furthermore, in situ resource utilization using local materials for construction and life support will be vital to reduce the dependency on Earth shipments and ensure sustainability. Infrastructure development is crucial for achieving a successful lunar base, which would require power generation solutions, communication systems, and transportation networks on the lunar surface. Considerations for energy sources include solar panels, which could provide power during the lunar day, but effective storage solutions would be necessary to manage energy during the prolonged lunar night. Communication with Earth must also be robust and reliable, ensuring that astronauts can communicate with mission control and have access to essential data. These challenges require innovative approaches, extensive research, international collaboration, and commitment on a grand scale. Addressing the complexities of establishing a permanent lunar base will provide valuable insights not only for sustainable lunar habitation, but also for future missions to Mars and beyond, as the skills and technologies developed could pave the way for human exploration of the solar system. Harnessing the resources of asteroids presents an exciting opportunity for advancing space exploration and potentially enabling sustainable human presence beyond Earth. Asteroids are rich in various materials, including metals, water, and other volatiles, which can be utilized for a range of applications in space. The prospect of mining asteroids could significantly reduce the costs associated with launching materials from Earth and foster a new era of resource utilization in space. One of the most critical resources found in asteroids is water, which can be extracted and processed into hydrogen and oxygen through electrolysis. This water is essential for sustaining human life, but it also has great potential for fuel production. Hydrogen can be utilized as a propellant, and when combined with oxygen, it can create rocket fuel for long-duration space missions. By establishing refueling stations in low Earth orbit or at lunar bases, spacecraft can refuel using water mined from asteroids, thus enabling deeper space exploration and reducing the need to carry all propellant from Earth. Asteroids are also abundant in metals and rare elements including platinum, nickel, and iron. These materials can be used not only for manufacturing equipment and structures in space, but also for building advanced spacecraft. The ability to mine and process metals directly in space means that missions could be less dependent on Earth-based resources, ultimately decreasing costs and logistical challenges. Advanced technologies for in-situ resource utilization will be crucial for extracting and refining materials on asteroids, and innovations in robotics and autonomous systems will enhance efficiency and safety during mining operations. Another aspect of asteroid resource utilization involves the potential for creating building materials. By processing asteroid regolith, we could manufacture bricks or other construction materials for habitats or infrastructure on the Moon, Mars, or orbital stations. This capability would support growing human settlements in space and reduce the need for transporting heavy materials from Earth. Challenges remain in effectively harnessing these resources, including developing proven extraction and processing technologies, ensuring the safety and sustainability of operations, and addressing the legal and ethical implications of asteroid mining under international space treaties. Nonetheless, As our technological capabilities continue to advance, the potential for creating a resource-rich environment in space becomes increasingly feasible, paving the way for future exploration and possible permanent human presence beyond our planet. Interstellar travel remains one of the most profound challenges in space exploration, requiring innovative propulsion technologies that can operate efficiently over vast distances. Several concepts have been proposed to make journeys to nearby stars feasible, many of which push the boundaries of current scientific understanding. One possibility is the development of fusion propulsion systems. Fusion drives operate on the principle of harnessing the energy generated by nuclear fusion reactions, similar to the processes that power the sun. This technology could provide a much greater thrust and efficiency than traditional chemical rockets. Concepts like the Project Orion, where nuclear bombs are detonated to propel a spacecraft, have been discussed, as well as more controlled approaches like the direct fusion drive, which utilizes helium-3 and deuterium fusion to produce thrust. The challenge lies in achieving the conditions necessary for sustained fusion reactions in a spacecraft environment. Another exciting concept is the use of light sails propelled by powerful lasers. In this method, a large reflective sail attached to a spacecraft could be accelerated by focused laser beams directed from Earth or from orbital stations. This technology was explored in the Breakthrough Starshot initiative, which aims to send small, lightweight probes to the Alpha Centauri system within a couple of decades. While lasers could accelerate these probes to a significant fraction of the speed of light, challenges remain in building the necessary infrastructure and ensuring that the delicate sails can withstand the massive energies involved. Antimatter propulsion stands out as a highly theoretical but tremendously powerful approach. Antimatter reactions release energy far more efficiently than conventional fuel reactions, producing significant thrust when matter and antimatter collide. This technology could enable a spacecraft to achieve a significant fraction of the speed of light, vastly shortening travel times to other star systems. However, the production and storage of antimatter remain substantial hurdles, as creating even tiny amounts of antimatter requires tremendous energy and advanced containment methods. Finally, the theoretical concept of the warp drive offers a fascinating glimpse into potential interstellar travel. Based on the principles of general relativity, a warp drive could bend or warp spacetime to allow a spacecraft to effectively ride a wave, enabling it to travel faster than light without violating the laws of physics. While the mathematics of warp bubbles has been proposed, practical implementation remains firmly in the realm of theoretical physics, requiring materials and energies that are not yet understood. These diverse propulsion technologies highlight the vast scope of research and innovation necessary to tackle interstellar travel. Progress in these areas not only enhances our understanding of physics but also inspires future generations to explore the cosmos and consider the possibilities of reaching distant stars. Building and maintaining space elevators presents a grand vision for future transportation in space, leveraging the concept of a tether extending from the Earth's surface into space. This structure would enable efficient and cost-effective access to orbit, providing a means to transport materials and people with reduced reliance on traditional rocket technology. However, the challenges associated with constructing a space elevator are formidable and encompass engineering, materials, science, and logistical hurdles. The core of the concept relies on the use of incredibly strong materials for the tether, which would need to withstand immense tensile forces. Current materials like steel or Kevlar are insufficient due to their weight and strength limitations. Researchers are exploring advanced materials such as carbon nanotubes and graphene, which possess remarkable strength-to-weight ratios. These materials could potentially enable the construction of a cable long enough to reach geostationary orbit around 36,000 kilometers above the Earth. The development of these materials must advance significantly before construction can begin, and production methods for creating large quantities of such materials at a low cost remain a focus of ongoing research. Once the materials are established, the design of the space elevator must consider various engineering challenges, including the anchoring of the tether to the ground and the mechanisms for ascent and descent. The base must be located at an optimal latitude and a stable location, such as a platform near the equator, to reduce the effects of Earth's rotation on the structure. An elevator climber, resembling a lift, would travel up and down the tether, requiring a robust power source for propulsion, which could be provided via laser systems that beam energy to the climber or other forms of advanced technology, such as magnetic levitation. Maintaining a space elevator also involves continual monitoring and upkeep to ensure its structural integrity and operational functionality. The tether would be susceptible to various threats, including micrometeoroid impacts, atmospheric conditions, and space debris. Regular inspections and potential repairs would be vital, along with a system designed to detect and respond to such hazards. Automated systems powered by artificial intelligence could be deployed to monitor the tether's condition, allowing for preventive maintenance procedures and minimizing downtime. The concept of a space elevator inspires intrigue and ambition, providing an emblematic goal for future space exploration. While the technical and engineering challenges are substantial, ongoing research continues to advance our understanding of materials and structures in extreme environments. With global collaboration and investment in innovative technologies, the dream of building and maintaining a space elevator could one day become a reality, revolutionizing our access to space and altering the way we explore the cosmos. The potential uses of artificial gravity in space colonization are numerous and could address some of the most significant challenges associated with long-duration space travel and habitation. Since prolonged exposure to microgravity can adversely affect human health, the introduction of artificial gravity through rotating habitats or centrifuge systems could help create environments more conducive to the physical well-being of astronauts and colonists. One of the primary uses of artificial gravity is to mitigate the adverse physiological effects of living in a microgravity environment. Extended stays in space can cause muscle atrophy, bone density loss, fluid redistribution, and cardiovascular changes. By simulating gravity through centrifugal force in rotating habitats, space colonists could maintain muscle mass and bone strength, reducing the risks associated with long-term space travel. This simulated gravity would help ensure that astronauts remain fit and healthy during missions to Mars, the Moon, or beyond, potentially enabling humans to live comfortably in space for years. In addition to health benefits, artificial gravity could facilitate daily activities aboard space habitats. Tasks such as cooking, eating, and sleeping might become more manageable in a setting where natural gravitational forces are simulated. This would allow colonists to use traditional furniture and appliances designed for gravity, making the living experience more familiar and comfortable. Consequently, integrating artificial gravity could help create a more Earth-like environment, enhancing the psychological well-being of space residents and potentially reducing the feelings of isolation often experienced in space. Artificial gravity could also impact agricultural practices in space colonization. Growing crops in microgravity presents unique challenges such as water distribution and the development of root systems. With artificial gravity, crops could be cultivated in conditions more similar to Earth, enabling better growth and optimizing food production for long-term missions or colonies. This would be essential for sustainability and self-sufficiency, as food supply dependency on Earth would be minimized. Finally, artificial gravity could play a role in experiments and research conducted in space. Many scientific experiments require certain physical conditions to yield accurate results, and simulating gravity would enable researchers to study a broader range of phenomena. From biological reactions to material sciences, having a controlled environment where gravity is present could enhance our understanding of various processes, leading to advancements in technology and materials that could benefit both space colonization and life on Earth. The implementation of artificial gravity could significantly improve the feasibility of space colonization, supporting human health, daily living, agricultural practices, and scientific experimentation. As humanity looks toward a future of exploration and habitation beyond our planet, understanding and applying the principles of artificial gravity will be critical in overcoming the challenges associated with life in space. Protecting space travelers from cosmic radiation during long journeys is a critical concern for ensuring their health and safety, particularly for missions beyond low Earth orbit, such as trips to Mars. Cosmic radiation consists of high-energy particles, including protons and heavy ions, which can penetrate spacecraft and pose serious risks, such as increased cancer risk, damage to the central nervous system, and other acute radiation effects. Several strategies and technologies have been proposed to mitigate these risks effectively. One of the fundamental approaches to radiation protection is the use of effective shielding materials. High-density materials, such as lead or specialized polymers, can absorb or deflect radiation. However, a more efficient method involves utilizing the materials available in space itself, known as in situ resource utilization. For example, surrounding spacecraft with lunar regolith or Martian soil as a protective layer could enhance shielding capabilities, while also reducing the need to carry heavy materials from Earth. Research into advanced materials, such as polyethylene or hydrogen-rich compounds, shows promise due to their ability to reduce radiation exposure significantly. Another innovative strategy could involve creating radiation bunkers within the spacecraft, designating specific areas reinforced with heavy shielding where astronauts can take refuge during intense solar events, or when cosmic radiation levels spike, can be an effective means of enhancing safety. These bunkers could be equipped with essential life support systems, allowing astronauts to stay temporarily during heightened radiation exposures. Moreover, continuous monitoring systems that assess radiation levels in real time would enable crew members to make informed decisions on when to seek shelter. Additionally, active radiation mitigation strategies are also being investigated. One such concept involves the use of magnetic or electric fields to create a protective barrier that could deflect high-energy particles away from the spacecraft. Research into plasma shielding and other electromagnetically based methods is ongoing, although practical implementation remains in earlier developmental stages. These active methods could be complements to passive shielding and provide an added layer of protection. Finally, careful mission planning plays a vital role in protecting space travelers from cosmic radiation. By considering the timing of solar events and designing missions to avoid periods of heightened solar activity, space agencies can minimize exposure risks. Continuous monitoring of solar weather and establishing protocols for adjusting mission operations accordingly will enhance astronaut safety. Overall, addressing the threats posed by cosmic radiation requires a multifaceted approach that combines advanced materials, effective spacecraft design, active mitigation techniques, and strategic mission planning. As our understanding of cosmic radiation and its effects continues to evolve, collaborative efforts in research and engineering will be crucial for developing effective protection strategies, ensuring the safety and well-being of astronauts on long-duration space missions. Artificial intelligence is poised to play a transformative role in the future of space exploration, enhancing our ability to conduct missions efficiently and effectively. As space missions become more complex and ambitious, incorporating AI technology can significantly improve decision-making, data analysis, and operational automation, allowing human explorers and robotic systems to work more seamlessly together. One of the primary applications of artificial intelligence in space exploration lies in data analysis. Space missions generate vast amounts of data from numerous sources, including telescopes, satellite sensors, and planetary landers. AI algorithms can process and analyze this data more quickly and accurately than human researchers, identifying patterns and anomalies that might otherwise go unnoticed. For instance, in the search for exoplanets, AI can help sift through data to recognize potential signals of planetary bodies around distant stars, thereby accelerating the discovery process. AI will also enhance autonomous systems for spacecraft and rovers. As missions venture farther from Earth, the communication delay can hinder real-time decision-making and operational adjustments. AI-powered systems can enable spacecraft to make critical decisions autonomously, allowing them to adjust trajectories, perform scientific experiments, and navigate unknown terrain without waiting for instructions from mission control. This autonomy is particularly crucial in environments like Mars or asteroids, where rapid responses to dynamic conditions may be necessary. In addition, artificial intelligence can play a significant role in mission planning and resource management. By optimizing spacecraft trajectories, fuel usage, and life support systems, AI can help ensure that missions are executed efficiently and safely. For instance, AI systems can assess the health and performance of onboard systems, predicting potential failures and suggesting preventive maintenance actions before issues arise. This proactive approach enhances the durability and reliability of spacecraft during long-duration missions. Moreover, AI can contribute to human-robot collaboration in space habitats. As astronauts live and work in space, AI can assist with day-to-day tasks, providing real-time insights and support for scientific work, maintenance, and health monitoring. Moreover, robotic assistants equipped with AI could perform routine chores, monitor astronauts' health, and ensure optimal living conditions, allowing human crew members to focus on more complex tasks that require creativity and problem-solving skills. Looking forward, the integration of artificial intelligence into space exploration will unlock new possibilities. By enhancing data analysis, enabling autonomous operations, optimizing mission planning, and fostering human-robot collaboration, AI will be an essential partner in humanity's quest to explore the solar system and beyond. As these technologies continue to advance, they will pave the way for a new era of space exploration characterized by efficient operations, accelerated discoveries, and the possibility of venturing further into the cosmos than ever before. Constructing large-scale habitats in space requires innovative approaches that address the unique challenges of the extraterrestrial environment. Whether the goal is to establish settlements on the Moon, Mars, or in orbit around Earth, various strategies can be employed to create safe, functional, and sustainable living conditions for astronauts and future colonists. One of the key methods for building habitats in space involves using in-situ resource utilization, or ISRU. This means utilizing the materials and resources available on site rather than transporting all construction materials from Earth. For example, lunar regolith or Martian soil could be processed to create bricks or other building components. This reduces the payload that must be launched from Earth, decreasing costs significantly and allowing for structural elements to be crafted using local materials. Research is currently being conducted on techniques such as 3D printing, which can create complex structures using regolith-based materials. Another concept for habitat construction involves modular designs. By developing prefabricated modules on Earth that can be assembled in space, it is possible to streamline the construction process. These modules can be launched individually and connected to form a larger habitat as needed, allowing for flexibility in design and function. This approach enables habitats to be expanded or rearranged over time, adapting to the evolving needs of their inhabitants. Such modular systems can provide essential living quarters, laboratories, greenhouses, and recreational facilities, creating a comprehensive living environment for astronauts. Additionally, considerations for protection against the harsh conditions of space are crucial in habitat design. Space habitats must provide sufficient shielding against cosmic radiation and micrometeoroid impacts. Designs that incorporate thick walls made from shielding materials or techniques such as burying habitats underground or covering them with lunar soil can enhance protection. Furthermore, maintaining a stable atmosphere and temperature within habitats will be essential for human health and comfort. Implementing closed-loop life support systems that recycle air, water, and waste will support long-term sustainability by reducing reliance on resupplies from Earth. Third, construction also requires a focus on energy generation and storage. Habitats will need reliable power sources, particularly in environments where traditional energy systems might not function effectively. Solar panels are a common choice for generating electricity, but energy storage systems will need to be developed to ensure that power is available during periods of low sunlight, such as the long lunar night. Advanced technologies, such as nuclear power systems, may also play a role in providing continuous energy for habitats. Ultimately, the construction of large-scale habitats in space encompasses a multifaceted approach involving the use of local resources, modular designs, robust protective systems, and reliable energy supplies. Collaborative efforts between governments, private aerospace companies, and international partners will be essential in overcoming the challenges of extraterrestrial construction, paving the way for sustainable living environments as humanity reaches further into the cosmos. Long-term human survival in the space environment poses several significant challenges that must be addressed to ensure the health and safety of astronauts during extended missions, such as those to Mars or permanent colonies on the Moon. These challenges span physiological, psychological, and logistical domains, highlighting the complexity of sustaining human life beyond Earth's atmosphere. One of the most pressing concerns is the impact of microgravity on the human body. Prolonged exposure to such an environment can lead to muscle atrophy, bone density loss, and changes in cardiovascular function. Without the constant resistance of gravity, astronauts can experience significant muscle weakening, and bone mass can decrease by as much as 1 to 2% per month. Developing countermeasures, such as specialized exercise regimens that simulate gravitational forces along with proper nutrition, will be crucial in mitigating these physiological effects and maintaining the overall health of astronauts. Another challenge is the exposure to cosmic radiation, which poses serious risks to human health. Unlike on Earth, where the atmosphere provides protection from high-energy particles, space travelers are exposed to galactic cosmic rays and solar particle events, increasing their risk of cancer, acute radiation sickness, and damage to the nervous system. Effective radiation shielding must be designed into habitats, and strategies for shielding astronauts during solar activity, such as utilizing safe regions or reinforced bunkers, will need to be implemented to minimize exposure. The psychological aspects of long-term space travel also present challenges. Isolation, confinement, and the stresses of living in a small group within a spacecraft or habitat can lead to issues such as anxiety, depression, and interpersonal conflicts. The lack of natural environments and social structures can exacerbate these challenges. Developing strategies for crew cohesion, effective communication, and mental health support will be essential in ensuring the well-being of astronauts during long-duration missions. Regular psychological assessments, recreational activities, and opportunities for personal space can help mitigate the effects of prolonged confinement. Additionally, logistical challenges related to resource management must be addressed for sustainable human presence in space. Systems for life support, including reliable water and oxygen supply and waste recycling, must be developed to operate efficiently for long durations. Propellant production using in situ resource utilization on planetary bodies can minimize the need for resupply missions from Earth. Ensuring that food is available over extended missions requires careful planning, including advances in food preservation, storage, and potentially growing crops in space. Achieving long-term human survival in the space environment involves overcoming a range of challenges related to physical health, psychological well-being, and logistical support systems. Continued research and innovation will be vital for developing effective countermeasures, sustainable practices, and support mechanisms to ensure that astronauts can thrive in the demanding conditions of space. As humanity expands its reach into the cosmos, addressing these challenges will be essential for successful missions and potential colonization efforts. Gravitational assists, also known as gravity assists or slingshot maneuvers, are a powerful technique used in space exploration to increase the speed and alter the trajectory of spacecraft without expending additional fuel. This method utilizes the gravitational field of a planetary body to steal some of its motion. allowing the spacecraft to gain energy and achieve trajectories that enable it to reach distant destinations more efficiently. The principle behind gravitational assists is based on the conservation of momentum and energy. When a spacecraft approaches a planet, it falls into the planet's gravitational field, accelerating as it gets closer. Instead of landing, the spacecraft then swings around the planet and is propelled forward as it escapes the gravitational influence. The relative motion between the planet and the spacecraft is crucial. As the spacecraft gains speed during the encounter, it can effectively slingshot away from the planet with a higher velocity than it had before. This technique has been employed in numerous deep space missions to conserve fuel and enhance travel distances. For instance, the Voyager missions utilized gravitational assists from multiple planets, Jupiter, Saturn, and others, to achieve extremely high velocities on their trajectories to the outer planets and into interstellar space. By carefully calculating the timing and path of these assists, mission planners can maximize the energy transfer, enabling spacecraft to reach destinations that would otherwise be too far or require impractically large amounts of fuel. In addition to increasing speed, gravitational assists also allow for trajectory adjustments. By planning a spacecraft's approach to specific planets, mission designers can alter its path to align with various celestial targets, such as asteroids or other planets. This flexibility enhances mission planning and enables exploration of diverse destinations, often with minimal additional cost. Gravitational assists can also extend mission lifetimes and capabilities. Spacecraft can use this technique to reduce travel times for distant targets, making missions more feasible and allowing for the potential inclusion of more scientific objectives. By utilizing the gravitational fields of multiple planets, future missions may include visits to various destinations in a single launch, maximizing scientific return while minimizing the fuel requirements. Gravitational assists are a fundamental maneuver in modern space exploration. By leveraging the gravitational energy of planets, spacecraft can achieve higher speeds, alter their trajectories, and conserve fuel, which in turn enables ambitious missions across the solar system and beyond. As mission technologies continue to advance, gravitational assists will remain a key strategy for exploring the far reaches of space. Nuclear propulsion holds significant potential for revolutionizing space travel, offering several advantages over conventional chemical propulsion methods. The two main types of nuclear propulsion concepts are nuclear thermal propulsion and nuclear electric propulsion, each presenting unique capabilities for future space missions. Nuclear thermal propulsion involves using a nuclear reactor to heat a propellant, such as hydrogen, which then expands and is expelled through a rocket nozzle, producing thrust. This method can achieve much higher specific impulse than chemical rockets, meaning it can produce more thrust per unit of propellant consumed. This increased efficiency translates to shorter travel times for missions to destinations such as Mars or other planets, making long-duration missions more feasible. For instance, a nuclear thermal rocket could potentially cut travel times to Mars from several months to a matter of weeks, thus reducing the exposure of astronauts to the hazards of space like radiation. Nuclear electric propulsion, on the other hand, utilizes a nuclear reactor to generate electricity, which is then used to power electric thrusters such as ion or Hall effect engines. This system provides continuous, low-thrust propulsion over extended periods. While it does not provide the same immediate thrust as nuclear thermal propulsion, it is highly efficient and capable of maintaining a steady acceleration for long durations. This makes it particularly well suited for deep space missions, such as those targeting the outer planets or asteroids, where spacecraft can build up significant speeds over time without needing to carry large amounts of propellant. In addition to increased efficiency and reduced travel times, nuclear propulsion technologies open up new possibilities for scientific exploration. The ability to conduct faster missions means that multiple destinations can be reached within a single mission, maximizing scientific return. Moreover, nuclear propulsion systems can enable more ambitious missions, such as crewed missions to Mars, permanent outposts on the Moon, or even human exploration of the outer planets. However, various challenges must be addressed before nuclear propulsion can be widely utilized in space travel. These include technical challenges related to the safe and reliable design of nuclear reactors for space use, public perception and regulatory concerns regarding the use of nuclear materials, and the need for significant investment in research and development to advance these technologies. Overall, nuclear propulsion presents a compelling option for the future of space travel, offering the potential to enhance mission efficiency and enable new explorative capabilities. As research continues and technology advances, nuclear propulsion may play a crucial role in humanity's quest to explore the solar system and beyond. Space telescopes like the James Webb Space Telescope are at the forefront of astronomical research, significantly pushing the boundaries of our observations and enhancing our understanding of the universe. JWST is specifically designed to observe the cosmos in infrared wavelengths, filling gaps left by its predecessor, the Hubble Space Telescope, which primarily observed in optical and ultraviolet light. By operating in the infrared range, JWST can see through dust clouds that often obscure celestial objects, enabling it to study previously hidden phenomena. One of the key advantages of observing in infrared is the ability to detect cooler objects. This capability allows researchers to examine the formation of stars and planetary systems, which often take place within dense clouds of gas and dust. By studying the wavelengths corresponding to heat emissions, JWST can capture images and data from young stellar nurseries, revealing insights into star formation processes and the early stages of planetary system development. Additionally, JWST's powerful capabilities facilitate observations of distant galaxies, enabling scientists to study the formation and evolution of structures in the universe over billions of years. As light from these galaxies travels vast distances, it is redshifted, moving from visible to infrared wavelengths. JWST is uniquely capable of detecting this redshifted light, allowing astronomers to peer back in time to observe the universe as it was just a few 100 million years after the Big Bang. This contributes to our understanding of how galaxies, stars, and galaxies evolved over cosmic history. The telescope's advanced technology also supports a wide range of scientific studies beyond just observing distant galaxies. For example, JWST can analyze the atmospheres of exoplanets, identifying chemical signatures that may indicate the presence of water, carbon dioxide, methane, and even potential biosignatures. This research plays a crucial role in the search for extraterrestrial life and expands our knowledge of the diverse environments in which planets exist. Furthermore, JWST's high-resolution imaging capabilities and sensitivity allow it to map and characterize structures within our own solar system, including the dynamics of planetary atmospheres and the composition of distant comets. This information aids in our understanding of planetary processes and evolution. Space telescopes like the James Webb Space Telescope push the boundaries of our astronomical observations by enabling us to see further into the universe, understand celestial phenomena previously obscured by dust, and gather unprecedented insights into the formation and evolution of stars and galaxies. The groundbreaking findings from missions like JWST will likely reshape our understanding of the cosmos and catalyze new discoveries for years to come. In situ resource utilization, or SRU, refers to the ability to harness and utilize resources found directly on other planets or moons, significantly reducing the need to transport materials from Earth for long-term missions. This concept is vital for sustainable exploration and habitation beyond our planet, particularly for NASA's Artemis program on the Moon and future missions to Mars. Various technologies are being developed to enable efficient ISRU processes, focusing on key resources such as water, oxygen, and construction materials. One of the most critical resources for ISRU is water, which can be found in frozen forms on the Moon and in subsurface ice on Mars. Technologies developed for extracting water include methods for obtaining ice and processing it into liquid form. For example, the use of drilling systems that can reach icy layers, followed by techniques to melt and purify the water, is being explored. Additionally, by employing advanced sensors, surface rovers can identify potential ice deposits and assess their composition, guiding future extraction efforts. Oxygen is another key resource, essential for both life support and rocket fuel. ISRU technologies aimed at producing oxygen on Mars include processes that extract O2 from the Martian atmosphere, which is composed of about 95% carbon dioxide. The Mars Oxygen In Situ Resource Utilization Experiment, part of the Perseverance rover mission, is a pioneering demonstration of this concept. MOXIE uses electrochemical reactions to separate oxygen from carbon dioxide in the atmosphere, providing insights into the feasibility of scalable oxygen production for future crewed missions. Another area of focus in ISRU development involves creating building materials using local resources. For example, lunar regolith or Martian soil can be processed to produce bricks or other construction materials through techniques such as sintering or 3D printing. Research is underway to develop materials that can be formed on site, allowing astronauts to construct habitats or infrastructure without relying on supplies transported from Earth. This not only reduces transportation costs, but also enables the establishment of more sustainable living conditions for long-term habitats. Additionally, technologies for the production of fuel and other consumables from local resources are being explored. Conversion processes, such as extracting hydrogen or methane from Martian soil or ice, can be combined with atmospheric extraction technologies to create propellants for return missions or further exploration. These methods are essential for reducing the dependency on Earth-based supplies and enhancing the overall sustainability of space missions. The development of technologies for in-situ resource utilization is crucial for future exploration and habitation on other planets. Efforts are concentrated on extracting water, producing oxygen, creating building materials, and manufacturing fuel from local resources. As these technologies advance and demonstrate effectiveness, they will significantly enhance the feasibility of sustained human presence and exploration beyond Earth, paving the way for future missions to the Moon, Mars, and beyond. Using lasers for interstellar communication presents a promising approach for transmitting information across the vast distances of space. Laser communication, or optical communication, capitalizes on the unique properties of laser light, including its ability to be focused into a narrow beam and travel long distances with minimal dispersion. This capability is particularly advantageous in the context of interstellar communication, where the challenges of distance and signal degradation must be addressed. One significant benefit of laser communication systems is their high data transmission rates. Compared to traditional radio waves, lasers can carry much more information, allowing for richer and more complex data exchanges, including high-resolution images and video streams. This increased bandwidth is essential for effectively communicating with interstellar probes or spacecraft that may be exploring distant star systems. For instance, missions like the recently proposed Breakthrough Starshot program aim to send tiny light-powered spacecraft to the nearest stars, such as Alpha Centauri, and lasers could facilitate high-speed communication with these craft as they transmit back valuable scientific data. Another advantage of lasers is their directionality. A laser beam can be collimated into a narrow stream, minimizing the risk of signal loss over long distances. In contrast, radio waves spread out over time, which can dilute the signal and make long-distance communication less effective. Laser communication could enhance the potential for receiving messages sent from distant civilizations, as they might be more easily focused and directed, thus improving the likelihood of picking up weak signals. However, using lasers for interstellar communication also presents challenges. One major hurdle is the need for precision in aiming and aligning the laser communication systems between sender and receiver, especially given the vast distances between stars. This requires sophisticated tracking systems to adjust for the relative motion of both the emitting and receiving entities. Additionally, Atmospheric interference, such as clouds or turbulence, can affect ground-based laser transmissions, although space-based systems would have fewer obstacles to contend with. Moreover, robust technology to encode and decode messages is essential for effective communication. Advanced modulation techniques would be required to convert information into a form suitable for laser transmission and ensure that the intended message is accurately received. This not only involves transmitting the laser signal, but also developing effective protocols for recognizing and interpreting the incoming data. As we continue to explore advancements in laser technology and improve our ability to harness their potential for communication, it becomes increasingly feasible to consider laser communication as a viable method for interstellar exchanges. Whether it be for sending messages to distant civilizations or for communicating with deep space probes venturing to the farthest reaches of our galaxy, the role of lasers in interstellar communication could open new avenues for understanding our universe and the possibility of extraterrestrial contact. Recent developments in spacesuit technology have focused on enhancing functionality, safety, and comfort for astronauts as they prepare for upcoming missions to the Moon, Mars, and beyond. One of the most notable advancements is the design of the NASA Artemis suits, officially known as the Exploration Extravehicular Mobility Unit. These suits are specifically crafted for lunar exploration and will allow astronauts to conduct surface operations with increased mobility and agility compared to previous designs. One significant improvement in the XEMU suits is their advanced mobility features. Unlike earlier models, which could be restrictive, the new design includes articulated joints and sleeves that allow for a greater range of motion. This is crucial for performing tasks such as collecting samples, operating tools, and conducting scientific experiments on the lunar surface. The suits incorporate a flexible torso system that allows astronauts to bend, twist, and move more easily while maintaining the necessary life support functions. Another critical advancement is in the life support systems integrated into the suits. The XEMU suits are equipped with improved ventilation and thermal control systems that help regulate temperature and manage moisture. This enhancement is particularly important as astronauts work in the extreme temperatures on the Moon, ranging from -250 degrees Fahrenheit at night to over 200 degrees Fahrenheit during the day. The new suits utilize innovative materials and technologies that manage heat more effectively, ensuring that astronauts remain comfortable while working outside their habitats. Additionally, advancements in communication technology have been integrated into the latest spacesuits. Equipped with improved communication systems, astronauts can maintain contact with mission control and other crew members while conducting extravehicular activities. This ensures that they can receive immediate guidance and support, enhancing safety during their operations. The communication systems have been designed to function effectively in the lunar environment, minimizing the potential for disruptions caused by background noise or other factors. A further focus in recent developments is on enhanced safety features. The suits are designed with multiple layers of protection against micrometeoroid impacts, radiation, and temperature extremes. Innovations in material science, including the use of specialized fabrics and composites, contribute to the overall durability and safety of the suits. Additionally, the XEMU design includes a helmet with a wider visor and improved heads-up display technology, providing astronauts with essential data and visual clarity while protecting them from harmful solar radiation. As exploration advances, there is also growing interest in the potential for future spacesuits for missions beyond lunar exploration, including Mars. Researchers are working on designs that will accommodate the different challenges posed by the Martian environment, such as atmospheric pressure, dust storms, and lower gravity. This forward-looking approach is essential for ensuring that astronauts can safely and effectively conduct operations on other worlds. The latest developments in spacesuit technology center on improving mobility, life support functions, communication systems, and safety features for astronauts. As we prepare for ambitious missions to the Moon and Mars, these advancements reflect a commitment to ensuring the well-being and effectiveness of those who venture into the complexity of space exploration. Nanotechnology holds tremendous potential to revolutionize space exploration by providing innovative solutions across various aspects of space missions, from materials and structures to health monitoring and energy systems. By manipulating matter on an atomic or molecular scale, nanotechnology can enhance the performance, efficiency, and capabilities of spacecraft and associated technologies. One of the most significant contributions of nanotechnology is in the development of advanced materials. Nanomaterials can be engineered to be lighter, stronger, and more resistant to extreme temperatures and radiation, making them ideal for use in spacecraft and habitats. For instance, carbon nanotubes and graphene may be utilized to create lightweight and durable structures that can withstand the harsh conditions of space while reducing overall launch costs. Improved materials can enhance spacecraft components, making them more resilient to micrometeoroid impacts and radiation exposure, ultimately increasing mission reliability and safety. In addition to structural enhancements, nanotechnology can improve energy generation and storage systems. Solar panels designed with nanomaterials can be more efficient at converting sunlight into electricity, enabling greater power generation for spacecraft. Furthermore, advanced battery technologies and energy storage systems incorporating nanocomposites can enable more efficient energy management and longer-lasting power supplies for missions. This capability is particularly crucial for long-duration journeys, where reliable energy sources are essential for life support, scientific instruments, and communication systems. Nanotechnology can also play a critical role in health monitoring and life support for astronauts during space missions. Nanosensors could be developed to continuously monitor physiological parameters and environmental conditions within spacecraft. These sensors could detect changes in air quality, radiation levels, and astronaut biometrics, providing real-time feedback that enhances crew safety and health. By enabling early detection of potential issues, such as harmful gas concentrations or health problems, nanosensors could be vital in maintaining a safe living environment during long missions. Moreover, nanotechnology can significantly influence in-situ resource utilization efforts, optimizing the extraction and processing of local resources on celestial bodies. For example, nanomaterials could enhance the efficiency of chemical processes used to convert regolith into usable materials for construction or life support. This ability to utilize local resources will reduce the need for resupplying from Earth, making future space missions more sustainable. Finally, in the realm of propulsion, potential advancements in nanotechnology might lead to the development of innovative propulsion systems. Concepts such as solar sails made with lightweight nanomaterials could allow spacecraft to harness solar radiation for propulsion, enabling efficient travel over long distances. This approach could be particularly useful for missions targeting distant planets or even interstellar exploration. In conclusion, nanotechnology offers transformative possibilities for space exploration by advancing materials, energy solutions, health monitoring, in-situ resource utilization, and propulsion systems. As research in this field continues to develop, the capabilities and sustainability of future space missions can be greatly enhanced. Embracing nanotechnology not only holds the potential for improved missions, but also paves the way for a new era in humanity's quest to explore the cosmos. Space-based solar power has emerged as a promising concept for harnessing renewable energy, particularly given the limitations of terrestrial solar energy systems, such as weather conditions and day-night cycles. By capturing sunlight in space, solar power systems could provide a continuous, reliable energy source that can be transmitted back to Earth or used in space applications. However, there are several challenges and potential benefits associated with this innovative approach. One of the primary challenges of space-based solar power is the complexity and cost of launching and deploying large solar arrays and associated infrastructure into orbit. Developing the necessary technologies and vehicles to transport the components safely and inexpensively is essential for the feasibility of such systems. The construction of solar power satellites or arrays in low Earth orbit or geostationary orbit requires detailed engineering and careful planning to ensure reliable operation, maintenance, and longevity in the harsh space environment. Additionally, the design and development of effective energy transmission technologies present significant hurdles. Solar power collected in space would need to be converted into microwave or laser energy for transmission back to Earth. Establishing a robust and efficient method for beaming this energy and subsequently converting it back into electricity upon reaching the ground poses both technical and safety challenges. Ground-based receivers must be designed to collect energy without causing harm to living organisms or disrupting existing infrastructure. The potential of space-based solar power, however, is substantial. One of the most significant advantages is the ability to capture solar energy continuously, regardless of terrestrial conditions. In space, solar arrays receive uninterrupted sunlight, leading to a consistent and reliable power output. This capability can significantly increase the efficiency of energy production compared to conventional solar power systems that are subject to atmospheric interference. Furthermore, space-based solar power systems could help meet the growing global energy demand while contributing to sustainability goals. By providing a continuous energy source, they could reduce the reliance on fossil fuels and help address climate change. The integration of space-based power systems into existing energy grids could enhance energy security and resilience, allowing for a more diversified energy supply. In addition to terrestrial applications, space-based solar power has significant potential for supporting future space missions. As space exploration expands, energy demands for habitats, spacecraft, and technologies will increase. Harnessing solar power in space could provide a sustainable energy source for future lunar or Martian bases, facilitating long-term human presence and exploration. While space-based solar power faces challenges related to deployment, energy transmission, and cost, its potential benefits in providing a continuous and sustainable energy source for both Earth and future space missions are substantial. Continued research and development in this area could pave the way for transformative advancements in energy production, with far-reaching implications for humanity's energy future and exploration of the cosmos. 3D printing technologies are being adapted for use in space, markedly transforming the way we approach construction, manufacturing, and sustainability for long-duration missions. The unique challenges of space environments necessitate innovations in additive manufacturing, enabling astronauts to produce needed tools, components, and even habitats directly on site, rather than relying on supplies shipped from Earth. One significant adaptation of 3D printing for space use involves the development of specialized printers that can operate under microgravity and utilize materials suited for the space environment. For example, researchers are exploring the use of lunar regolith and Martian soil as feedstock for 3D printing. These materials can be processed to create structural components, reducing the need to transport heavy construction materials from Earth. By leveraging local resources, 3D printing supports in situ resource utilization, promoting self-sufficiency in future lunar and Martian colonies. The design of 3D printers for space is also focused on compactness and the ability to operate autonomously or remotely. Space missions face constraints regarding weight and volume, necessitating printers that can be easily transported and set up in limited spaces. Innovations in the design of printers, such as those developed by companies like Icon and Redwire Space, allow for efficient operation and reliability in the harsh conditions of space. These printers are engineered to handle the specific challenges of microgravity, ensuring that the printing process remains controlled and precise. One of the most exciting applications of 3D printing in space is the potential to create complex geometries and customized parts on demand. This capability means that astronauts could manufacture replacement parts, tools, or even habitat components as they are needed, rather than stocking an extensive inventory aboard the spacecraft. For instance, NASA has successfully tested 3D printing to produce various tools and mechanical parts on the International Space Station, demonstrating the technology's practicality in real spaceflight operations. Moreover, advancements in bioprinting technologies may lead to innovations in healthcare and life support in space. Future applications could include printing living tissues or organ structures for medical purposes, enhancing astronauts' health and well-being during long-duration missions. Researchers are exploring the feasibility of using bioinks, which can encapsulate living cells to create functional biological materials, opening up new frontiers for space medicine. 3D printing technologies are being extensively adapted for use in space, enabling sustainable construction and manufacturing using local resources. By offering on-demand production capabilities, enhancing self-sufficiency, and addressing logistical challenges, 3D printing holds the key to addressing the unique demands of living and working in space. As research and technology continue to progress, the role of additive manufacturing in future space exploration and habitation will likely expand significantly, providing innovative solutions for a variety of challenges faced by astronauts. Swarm robotics could play a transformative role in future space missions by enabling collaborative operations among multiple robotic agents that work together to achieve complex tasks. This approach is inspired by the behaviors observed in natural swarms, such as those of insects or birds, and offers several advantages over traditional single robot systems, particularly in the context of exploring distant planets, moons, and asteroids. One of the primary benefits of swarm robotics is scalability and flexibility. A swarm of small autonomous robots can be deployed for various tasks, such as surveying terrain, conducting scientific experiments, or constructing habitat. Each robot in the swarm can operate independently while simultaneously communicating and coordinating with others, allowing for efficient data collection over large areas. This capability is particularly useful for planet-wide explorations or when detailed surface mapping is necessary. For example, swarms could be utilized to identify optimal landing sites, assess resources, and analyze geological features. Moreover, swarm robotics enhances redundancy and resilience. If one robot in a swarm fails or encounters obstacles, the remaining robots can continue to operate and complete the mission without significant disruption. This robustness is essential for space missions, where repairs may be challenging or impossible. By using multiple robots, mission planners can ensure that critical tasks can be completed even in the face of hardware failures or unexpected circumstances. Swarm robotics can also improve efficiency in resource utilization and energy management. Each robot can be designed to perform specific tasks and allocate energy resources effectively. For instance, some robots could focus on resource gathering, while others assist with construction, reducing the overall workload and optimizing energy consumption across the swarm. This adaptability means that swarm-based missions can operate longer and accomplish more within the constraints of available energy, such as solar power collected during surface operations. In the context of construction and in situ resource utilization, swarm robots could work collaboratively to build habitats, repair equipment, and manufacture components using local materials. For example, a swarm might be employed to gather lunar regolith and form building materials, constructing structures more efficiently than a single robot could accomplish alone. Additionally, the cooperative nature of swarms allows for real-time adjustments and improvements to construction plans based on environmental conditions or evolving mission goals. Finally, swarm robotics can play a crucial role in scientific research and exploration. With multiple robots equipped with sensors and instruments, swarms can efficiently gather diverse data sets from different locations, enabling scientists to analyze planetary environments more comprehensively. The collaborative capability means that researchers can undertake extensive surveying, atmospheric sampling, or geological assessments that would take considerably longer with a single robot. The potential of swarm robotics in future space missions lies in their ability to work collaboratively, improve efficiency, enhance redundancy, and enable complex tasks that would be difficult for traditional robotic systems alone. As research and technology advancements continue, swarm robotics could become invaluable for missions to the Moon, Mars, and beyond, facilitating exploration, scientific discovery, and sustainable habitats in the solar system.